Hey guys, and welcome to this video. In this video, we'll be working on the Mathematics Paper 1 for June 2025, and this is specifically from the Gauteng province. This paper is worth 150 marks, and the time allocated is 3 hours. Remember to round off to 2 decimal places unless stated otherwise, and the diagrams are not necessarily drawn to scale. Okay, with that being said, let's get into this video. Question 1, 1.1.1, we've been told to solve for x, but given a binomial, so not a trinomial as usual. So in order to solve for x here, we still have to factorize this, but we can factorize this using highest common factor. So between x squared and 4x, what is our common factor, highest common factor really? It would be x. So we take that out as a common factor, and what is left in the first term? We'll be left with x. And in the second term, we'll be left with positive 4. So this is equal to 0. And so it's still this whole idea of we have a value multiplied by another value, and they give us 0. So it's either the first is equal to 0 or the second is equal to 0. So that means that either x equals 0 or we have x plus 4 being equal to 0. And if you transpose, x equals negative 4. And those are our answers. Moving on to the next question. Question 1.1.2, we have to solve for x, but correct to 2 decimal places, meaning our x values, our solutions, will be irrational values. Okay, so we're going to have to use the quadratic formula if this is a quadratic equation. Now, it is because we can see that the highest exponent, okay, of x is 2. So it's just not in its standard form, meaning 3x needs to come over. So we're going to have 2x squared minus 3x minus 1 over 2 is equal to 0. And we can finally use the quadratic formula, which looks like this. So this is equal to, we'll say x is equal to negative b, which is negative 3. So negative 3 plus minus the square root of negative 3 all squared minus 4, and then a is 2. And c, we can see that is negative 1 over 2 all over 2a, which is 2. And so let's go ahead and find out what the first value is, okay, when we use the plus. Okay, so the first in decimal form is 1 point, and that's just going to round down to 65. Or, and when we change that to a minus, the second solution is where x is equal to negative 0.15, rounded down to 2 decimal places. Okay, so those are our answers, and moving on to the next question. Question 1.1.3 says we need to solve for this inequality. So solve for x in this inequality, and straight away we can see it's not in its standard form because it's quadratic. So this is now 3x squared plus 5x minus 2 is greater than or equal to 0. And let's factorize. So I'll use the cross method here, meaning we're going to take the factors of the first term. What times what gives us 3x squared? That's 3x times x. And then we need factors of 2. But they should help to give us a positive 5 in the middle while maintaining this as negative 2. So factors of 2 is 2 and 1. But if you put it like this, it's not going to help because we're going to multiply, and that's 3x. And then cross multiply there, and that's 2x. But you see, these will not help to give us a 5 in the middle if one of these have to be negative and one has to be positive. So here's how we can just rewrite this. Put it as 1 and 2. Okay, so when we multiply 3x times 2, that gives us 6x, and x times 1 gives us x. Now, in order to maintain this as positive 5x, we can leave this as positive and make this negative, because 6x minus x is positive 5x. Okay, so if this needs to be negative, how did we get the x in the first place? We got that by saying x times 1. So that takes the negative and that takes the positive. Okay, and now we can finally see that the factors are 3x minus 1 and x plus 2 is greater than or equal to 0. Okay, and let's go ahead and solve now. Okay, so looking at the quadratic expression, this is going to form a parabola, specifically a concave arc parabola, since the coefficient of x squared is positive. So it's a concave arc parabola, and then we have our x-axis, And we need our critical values. So to find the critical values, it's really just like making these factors equal to 0. So if 3x minus 1 is equal to 0, you transpose that -1 to make it positive and divide both hand sides by 3 to get an x value of 1 over 3. So the first critical value we have is x equals 1 over 3. And the second one is here when you transpose the 2. So x plus 2 equals 0. So x is equal to -2. Okay, so looking at it like that, we can see that the negative is over here. That's -2. And that's positive 1 over 3. Now, the inequality specifically says we need to find the values of x for which this graph or this expression is going to be greater than or equal to 0. Where this graph has values greater than or equal to 0 would be referring to the y values of this graph because they are a result of substituting x. So if we had a y-axis, so we can find out or pinpoint where exactly these y values which are greater than or equal to 0 are, they would be here. This is where we have positive y values or a y value equal to 0 right there. Okay, so we're only going to look at the parts of the graph that lie above the x-axis because all of these points would always map to y values that are positive. And of course, we're going to look at the one that is equal to 0. Okay, so we can just go ahead and erase that and we're only going to consider every part of the graph above the x-axis and of course on the x-axis. Okay, so it's greater than or equal to 0. So when we are answering them, we're going to just look at the direction of these points or these values, these x values. So if we line these down to the x-axis, you see that there are values that are moving to the left-hand side of -2. So it means that x is less than or equal to -2. Because at -2, the y value itself is 0. Okay, if you take -2 and substitute it into this equation, you'll get a y value of 0. And then looking at this part's x values, if you line these down to the x-axis, you see that these are values that are moving towards the right-hand side of 1 over 3. Meaning here, we're saying that x is greater than or equal to 1 over 3. Okay, it's equal to 1 over 3 for the same reason. And that is our answer. We can see that they are pointing in two complete opposite directions. They're not pointing towards each other, so we do not have to write them as one single inequality. Okay, and that is our answer. Moving on to the next question. The next question, 1.1.4, we have an exponential equation. We can see that because x is in the exponent. But in this equation, we have a repetition of a specific value, and that is 2 to the power of x. We see that here, 2 to the power of x. Of course, there's a 2 in front of it here in this case, but it's also here, 2 to the power of x. Now, it's a repetition of 2 to the power of x, but in front of one of those repeated values, there's a 2 there. Okay, so what we're going to do is we're going to use the k method substitution for this, just to make it simpler. So this is one of those ones that can actually become a quadratic equation. So we'll say, let k be equal to that repeated value, 2 to the power of x. And then in place of 2 to the power of x, we replace that with k. So that says 2 to the power of 2x, but you could have written that as 2 to the power of x times 2. So if this is k, then that's really just k squared. So k squared plus, and that's 2 to the power of x, so we replace it with k, minus 6 is equal to 0. And there we go. So how you would know it's this situation where you can straight away just use k method substitution is when you firstly see there's a repeated value, but in front of one of the repeated values, you have a 2, okay, in front of that exponent. So you know it's going to become quadratic. Okay, so with this, let's go ahead and factorize this equation. So open up two brackets, equate to 0, and we're saying what times what gives us k squared, that's k times k. And what times what gives us -6, that is 3 and 2. And those are the ones that will be more likely to give us a positive coefficient of 1 in the middle. So if we keep the 3 as positive 3 and we make the 2 negative, so that we can say positive 3 times -2 give us -6, then we know so positive 3 minus 2 is positive 1, which is indeed the coefficient of k. Okay, so this means that k is finally equal to -3, or k is equal to positive 2. And now that we know that, we're trying to solve for x, not k. So replace what k was back into this equation. So we're saying in place of k, 2 to the power of x is equal to negative 3, or 2 to the power of x is equal to 2. Now, in this equation, 2 to the power of x equals negative 3. Is this possible? Let's see. If you said 2 to the power of a value, can you ever get a negative number? Okay, if this was 2 to the power of negative 1, for example, we get a half. 2 to the power of negative 2, we get a quarter. So you see how this can never become negative? Even 2 to the power of 0 is 1. And then 2 to the power of any other positive number will just stay positive, okay? So this is not possible. You cannot take a positive base and raise it to an exponent and then it becomes negative. So we can just go ahead and tell them that these are not equal. We don't have a solution here. X has no solution. We'll just make that, cancel that. And then here we're saying 2 to the power of x is equal to 2. But then there's actually an exponent here. It's an invisible 1. So you see how the bases are exactly the same? So for this equation to really be true, the left and the right to be equal, then x should be equal to 1. So therefore x is equal to 1 only. And that is our answer. Moving on to the next question. Question 1.1.5, we have x squared minus 2x plus 3 plus 2 over x squared minus 2x is equal to 0. And we need to solve for x. Okay, so in this equation, you could try to solve for x by taking this over and then saying, okay, we're going to cross multiply. But that's going to complicate things because you see, if you try to do that and you leave this as, okay, one term with a denominator of 1. Okay, so it now becomes one single term like that. And you take that over, so it's negative 2 over x squared minus 2x. And you try to cross multiply. You see that when you cross multiply with this and this, you've got an x squared and an x squared. You're going to have an x to the power of 4, meaning that's an equation with 4 possible solutions. It's going to become complicated for you to now factorize that. So here's what you should do at this point. Notice that x squared minus 2x is being repeated. Here it is on the denominator. So we're also going to use the k method in this situation where we see a repeated value, which we could just simplify to k so we can solve for k and then we can actually just find out what exactly x is when we substitute it back. Okay, but just keep in mind how, we had x to the power of 4, meaning there's 4 possible solutions because that will be the highest exponent of x. Okay, so we're going to say let k be equal to x squared minus 2x. And so we have k, okay, in place of that. So say k and then plus 3 plus 2 over k is equal to 0. So looking at this equation, this is a situation where we just have k in the denominator. The k in the denominator is a problem. So we need to get rid of that. And in order to do that, you can just multiply both hand sides of this equation by k. So that's what's going to get that k out of the denominator because you're multiplying by a k. So diagonally, they will cancel. And they really just cancel because if they will multiply together, like if this was a and b, it just becomes ak over bk. And so you see how k's cancel. Okay, so now they'll distribute and we have k squared plus 3k. And then that is just plus 2 is equal to 0. And you see how we have a quadratic equation. So let's factorize this equation and solve for k. So k times k give us k squared. And then factors of 2. It's very simple in this case. Everything is positive. So this is positive 2 and positive 1. Therefore, k is equal to negative 2 or k is equal to negative 1. Okay, so now remember how k is equal to x squared minus 2x. We're going to put it back there because we're trying to solve for x, not k. So this is x squared minus 2x equals negative 2. Or we have x squared minus 2x being equal to negative 1. See how we have two trinomials? Okay, so each of them have 2 possible solutions. And that's why when we multiplied at first, we had an x to the power of 4. That was going to be the highest exponent of x, meaning you have 4 possible solutions. This is the reason why. You see, you have 2 possible solutions here, 2 possible solutions here. So it's a total of 4 possible solutions in this equation. Okay, so let's simplify this. This is now x squared minus 2x. And when we transpose that, that is plus 2 is equal to 0. And same thing here, x squared minus 2x, and that becomes plus 1 is equal to 0. So can we factorize this? If you say x times x, and then factors of 2 that give you negative 2, you won't find those. And for you to prove that you can't find those, you can actually, instead of using the quadratic formula, because if you use the quadratic formula, you're just not going to get any roots. So here's what you can do. Instead of using the quadratic formula, show that this cannot be factorized. We don't have any solutions by finding the discriminant. So the discriminant is b squared minus 4ac. And so we can see that this is the value of b. It is negative 2, and then a is positive 1, and c is positive 2. Okay, it's in the form of ax squared plus bx plus c, because this is a quadratic equation. Of course, is equal to 0. So we'll simply say negative 2 squared minus 4, and then a is 1 and c is 2. And let's see what this gives us. So that's going to be 4 minus, now these together, that's negative 4, and then times 2 is negative 8. So that's 4 minus 8. You see how that gives us negative 4? So because the discriminant b squared minus 4ac, okay, is less than 0, because that value is less than 0, we will not have any solutions here. So we'll say x has no real solutions. Okay, we will not have any real solutions here, and that is that one. So that ends there. And now we can look at this second equation. Okay, so factorize this equation, open up two brackets, equate to 0. X multiplied by x give us x squared. Factors of positive 1 that can give us a negative 2. You can either say positive 1 times positive 1, but you see that's not going to give you a negative 2. So if you made them both negative, then when multiplied, they give you positive 1. But when you say negative 1 minus 1, it does give you negative 2. So that's minus 1, minus 1. And you see that these are the exact same brackets, the same factors we have. So this is an example of an equation with the same root. You know how we say if the discriminant delta is greater than 0, then you have two different roots. And then if it's equal to 0, you have the same root. This is an example of that. Okay, so it just means that it's a repeated factor. So basically one root. So here, x is simply equal to, if you say x minus 1 equals 0 and transpose the negative 1, x is equal to 1. And that is our answer. We have only one x value that actually works for this equation. One real x value. Okay, so x is equal to 1 in this equation. And moving on to the next question. The next question, 1.1.6, we have an equation with a surd. So let's go ahead and isolate the surd, because the whole point is to solve for this equation. And right now, this is a problem. So we're going to leave this on this side. X plus 5 is equal to, and if we transpose this negative x, it becomes positive x, and we have minus 1. And now we can finally sort out this problem. So it's a square root. To get rid of the square root so we can properly solve for x, we're going to have to use the inverse of square rooting, which is to square. But this is an equation, so what you do on the one side, you must do on the other side. So this is now x plus 5 is equal to, see they break open because they are the inverse of each other. And here we can square that. So the first term squared is x squared. Last term squared is positive 1. First times second term is negative x, and then you need to times that by 2. So that's negative 2x. Okay, and now let's just transpose that. So we'll say that this means x squared minus 2x, and then minus x, and plus 1 minus 5 is equal to 0. Okay, so that just means that x squared minus 3x, and then 1 minus 5 is negative 4, is equal to 0, and we can factorize. So open up two brackets, equate to 0. What times what gives us x squared? That's x times x. And then factors of negative 4, that can give us a negative 3. So we can use 4 and 1, but now one of it needs to be negative, so it can multiply to become negative 4. But we need to give the negative in such a way that the middle term stays negative 3. So give the negative to the bigger factor. So that's negative 4 plus 1. And so therefore, x is equal to 4, or x is equal to negative 1. Okay, so we've got two values. But here's the thing about this equation with this surd. Initially, when we looked at this equation, right? And you looked at the highest exponent of x. What was that? The highest exponent of x was that invisible 1. So meaning you have one possible solution. So squaring both hand sides could have actually tampered with your solution. So you still need to check whether these are valid answers. And how we'll check is we'll take the original equation, right? We can take it like that x plus 5, as long as you take it at the point before it was squared, then it's fine. So we'll take this, and in place of x, we'll try substituting these values. Let's try 4 first. If we put 4 here and 4 here, does it really give us -1? Okay, 4 plus 5 is 9. Square root of 9 is 3. So that's 3 minus 4, which is -1. So that works. Okay, let's try -1. Let's try -1 here. This is minus -1. So you see how that becomes a plus. So we're saying 5 minus 1 is 4. And then square root of 4 is 2. And this is going to multiply to become a plus 1, which is 3. See how 3 and -1 are not the same number. So the left-hand side is not equal to the right-hand side for x equals -1. Okay, so cancel out the invalid solution and accept the valid. So we say x is not equal to -1, but x is equal to 4. And that is our answer. Moving on to the next question. Question 1.2 says solve for x and y simultaneously. So we have two equations and we need to solve for x and y. Always take the linear equation, okay, the one without any squares, any x times y's, anything like that. That's your linear, and make that the subject. If there's no linear, you just take the equation that it's easier to make a variable the subject. So we take that equation and we are going to take it further so we can make something the subject in it. In this case, x is easy to make the subject since it's just on its own, it's just x. So we'll leave x on the left-hand side and transpose the 2y. So this is equal to 5 minus 2y. And we can go ahead and say this is our equation 1, and we are going to substitute it into our equation 2. So substitute equation 1 into equation 2. So every time you see x in equation 2, replace it with 5 minus 2y. So that is 2y squared minus, and there's our x. But you see that there's a y after it. So it's going to be awkward to say 5 minus 2y and then y. So just rewrite it as minus y times 5 minus 2y minus 4. And then we have x again. So we're going to say times 5 minus 2y and squared is equal to 8. And now we're solving for y. So this is 2y squared, and distribute here. That's negative 5y positive 2y squared. And this now, you see that it has a squared. So you need to first distribute what is squared. So we have minus 4, and then times the first term squared is 25. The last term squared is positive 4y squared. First times second term is negative 10y. Then you times that by 2, which is negative 20y. And then we have is equal to 8, but we can just transpose that. So it's minus 8 equals 0. Okay, and now we just have to distribute here. So 2y squared plus 2y squared is 4y squared. And we have minus 5y, and let's distribute. So that is negative 100 and positive 80y, and then minus 16y squared minus 8 equals 0. Just like terms together, really. Okay, so 4y squared minus 16y squared is negative 12y squared. And then these two together, they really just become, okay, so that's 80 minus 5, which is 75. So positive 75y, and negative 100 and minus 8, which is negative 108, is equal to 0. Okay, not your prettiest looking equation, but you see that we have these values, negative 12, 75, and 108. Okay, negative 108. What do they have in common? They are numbers that are divisible by 3. So we can just divide both hand sides, because this is negative in front, the y squared. Just divide both hand sides by negative 3. And so we have, that becomes positive 4y squared. Negative 75y divided by 3 is negative 25y. And then negative 108 divided by negative 3 is positive 36. And just make sure that the signs are all correct. Okay, so it's equal to 0. And now we can finally factorize, if possible, of course. Okay, so let's take the factors of 4y squared. That's 4y times y gives us 4y squared. And then we need factors of 36, but we need to distribute this well. So just look at the numbers that give you 36. So 36, and let's just say shift fact, just to see our factors here. So we have like 4 and 9. Let's just try 4 and 9. Okay, so 4 and 9, but you see that only the middle is negative, meaning both of these values will be negative. Let's try to cross multiply and see whether we get this middle term of negative 25y. So 4y times negative 9, okay, that's 18 plus 18, which is negative 36y. And then if you say y times negative 4, that's negative 4y. That is not going to give us 25. It's too big. Okay, so let's just switch these around. Make that the 9 and that the 4, and then try again. So now that is negative 16y and negative 9y, which indeed does give us negative 25y. Okay, so 4y minus 9 and then y minus 4 equals 0. Okay, so now we can finally solve for y. So this means that we can have 4y being equal to 9, okay, because it's minus 9 equals 0, so equal 9. And then divide both hand sides by 4, meaning y is simply equal to 9 over 4, okay, or y is equal to positive 4. So we have our two values for y, and now we just need to find x. So use equation 1. It had x as a subject, so we're just going to substitute each of these y values into this equation. So this means x is equal to 5 minus 2 and then times 9 over 4. So x is equal to, when we multiply, the 2 cancels, so that is just 5 minus 9 over 2. Okay, you can just see that as times 2 is 10 over 2, which is 1 over 2. Okay, so x equals a half. Or here we're going to say 5 minus 2 times 4, and those give you negative 8. So 5 minus 8 is 3. So x is equal to negative 3, okay, because it's 5 minus 8, so negative 3. And there we go. These are our answers. X is equal to a half and y equals 9 over 4, or x is equal to negative 3 and y equals 4. Moving on to the next question. Question 1.3 says, for which values of k will the roots of 6x squared plus 6 equals 4kx be real and equal? Okay, so here's the criteria for real and equal roots. For the roots to be real, the discriminant simply just needs to be greater than or equal to 0. And then it's going to be real. Okay, if it's equal to 0, you have real roots. If it's greater than 0, you have real roots. You just will not have real roots if your roots are less than 0, okay? Because that discriminant is the part in the quadratic equation that we square root. That's square root b squared minus 4ac. So you're square rooting a negative number, which makes it non-real. Okay, so this is what we're looking for, right? For it to be real and equal. Now, for it to be equal, they didn't say unequal. So if we make it greater than 0, this will also include unequal roots. They want it to be real and equal. So we just need to make delta equal to 0. Okay, so the discriminant is equal to 0. So let's find that discriminant in this equation. We have 6x squared plus 6 equals 4kx. It's a quadratic equation, but it's not in its standard form. So put it in its standard form by transposing 4kx. So we have 6x squared and then minus 4kx. See how this is the coefficient of x, okay, negative 4k. And then we have plus 6 is equal to 0. So it is in the form of ax squared plus bx plus c equals 0, a quadratic equation. And now to tell them for which values of k this will be real and equal, we need to ensure that the discriminant is equal to 0. This will give you real and equal roots. Okay, so b squared minus 4ac simply needs to be equal to 0. And let's substitute. So b squared, you see how this is b, the coefficient of x. It's negative 4k. So we'll say negative 4k all squared minus 4 times a, which is 6, times 6, and then this is equal to 0. Okay, and we're just solving for k here. So that is just going to be positive 16k squared. And if we multiply 6 times 6 is 36 times 4. So that's 72 times 2, which is 144. Okay, so negative 144 is equal to 0. Okay, so now we can finally just solve. So this is an equation with difference of two squares. You see how that's a square value? That's also a square number, okay, 144. 12 times 12 is 144. So we can open up two brackets, or you could actually just solve it like this. So we could just solve it like this. 16k squared and transpose the 144. So it's now positive. And then divide both hand sides by 16. So therefore, k squared is equal to 144 divided by 16 is 9. So that's 9. And then square root both hand sides of the equation. If you square root and you square root, it's an equation. So you need to consider the positive and the negative solution. Therefore, k should either be equal to positive 3 or k should be equal to negative 3 so that you have real and equal roots for this equation. Okay, remember that the reason it's positive and negative is because it's not only 3 squared that give you 9, okay? Negative 3 squared is also equal to 9, and this is an equation. So those are our answers. K is equal to 3, or k is equal to negative 3, and that is it for question 1. Question 2.1 says, the first three terms of an arithmetic pattern are negative 5, 2, and 9. And 2.1.1 says we need to write down the next two terms of the pattern. Okay, so looking at our pattern, do you see that it is an arithmetic pattern? So that would mean that it has a constant difference. So we can just find that constant difference by saying 9 minus 2, term 3 minus term 2, which is 7. And so that means that each term would be found by adding 7 to the previous term. So it means that the next two terms would be 9 plus 7, which is 16, and then 16 plus 7, which is 23. And that is our answer. Okay, moving on to the next question. Question 2.1.2 says, show that the sum of the first n terms of the pattern is given by this formula. So we need the sum of the first n terms. So we're still using the sum, meaning we could use these two formulas. Okay, so any of these two formulas, but you see that we're trying to find the sum of the first n terms, meaning the last term will also just be the nth term. Okay, meaning that Tn equals a plus n minus 1. So we might as well just go with this one. Okay, because we're still going to get to this point. If you say first term plus last term, well, the last term is a plus n minus 1 times d. So it's still going to be the exact same thing. So let's go ahead and use this formula. So we're saying Sn is equal to, we still have n over 2 because we're trying to find the sum of the first n terms. And then 2a, now what is the value of a? A is the first term, and we can see that our first term here is negative 5. So we're going to say 2 times negative 5 plus n minus 1 multiplied by d, which we found to be positive 7. So multiply by positive 7. Okay, and now we just have to simplify this. So it means that Sn is equal to n over 2. And when we multiply these, they give us negative 10. And when we distribute here, we're going to get, let's just distribute with the negative 1 first. That's minus 7 and then positive 7n. Okay, and just rewrite it with the 7n being first. So therefore, Sn is equal to n over 2 multiplied by, and we have 7n, and negative 10 minus 7 is minus 17. And this is the answer. Just notice that they made that 1 over 2. It just means that there is an invisible exponent of 1 in front of n. So you could have also just rewritten that as 1 over 2 n. And this n would still be a value that is in the numerator because it has a invisible denominator of 1. Okay, so that is our answer. And moving on to the next question. Question 2.2 says, the first 4 terms of a quadratic pattern are x and then 3x minus 5, okay, and so on. So we have 4 terms and they want us to determine the value of x. Okay, so let's rewrite our pattern first. And now, in order to find x, we're going to use the fact that we know that the second constant difference is constant. And so that's where we're going to create an equation. So first, we need to find the first differences of this pattern. So we'll say the next term minus the previous term. So that is 3x minus 5 minus the x. And of course, that's going to simplify. So you see the 3x and the minus x, they'll simplify to 2x. So we have 2x minus 5 over there. We can just rewrite it here. That's fine. And then here we're subtracting 4x minus 3 and then minus this. So that's 4x minus 3 minus 3x minus 5. And when we distribute, we have 4x minus 3 minus 3x plus 5. And then 4x minus 3x is x. And we have 5 minus 3, which is positive 2. And you see that that simply just simplifies to x plus 2. And then we'll say next term minus previous term. And that's 5x plus 1 minus 4x minus 3. Okay, we're subtracting by something that has two terms, so we use brackets. And that is now 5x plus 1 minus 4x. And then that becomes a plus 3. And when we subtract that, that becomes x. And 1 plus 3 is positive 4. Okay, so we have x plus 4. And these are now our first differences. Okay, so now what can we do with this? This is our first differences of the quadratic pattern. It forms an arithmetic pattern, a linear pattern. So that means that if you find their differences, they will be constant. So whatever this term minus this term gives us is going to be exactly equal to this term minus this term. And so we'll find out by saying this is x plus 2 minus, and now I'm just going to apply that negative into each of these terms. So that's minus 2x, and then minus negative 5 becomes plus 5. So we'll have negative x, and then 2 plus 5 is a 7. So 7 minus x is what we have there. So 7 minus x, and here we're saying x plus 4 minus x minus 2. So you see how the x's cancel, and 4 minus 2 is 2. So we now know that these two should be equal. So our equation here is 7 minus x is equal to 2, and we're just going to solve for x. Transpose the x, it becomes positive. Transpose the 2, it becomes minus. So 7 minus 2 is 5. Therefore, x is equal to 5. And that is our answer. Moving on to the next question. Question 2.2.2 says, if the pattern continues indefinitely, prove that all the terms of the pattern are positive. The main thing that we can use to determine the kind of term values we're going to have is the general term. So we clearly have to find this pattern. So it's in the form of an squared plus bn plus c. Okay, so in our pattern, we're just going to have to concentrate on these three first terms. Okay, in the quadratic pattern, the first differences, and in the second constant difference, given that we know what x is now. Okay, so in each of these, this is what we're going to do. So the second constant difference, we're going to make this equal to 2a. And then the first difference, the first term in the first difference will be equal to 3a plus b. And then this will be equal to a plus b plus c. And we're only equating it to the first term in each. Now, in this one, it's quite simple because we already know what that second constant difference is. So we'll just say 2a equals 2. So if 2a is equal to 2, what is a equal to? A would simply be equal to 1 if you divide both hand sides by 2. And 3a plus b equals 2x minus 5. So this is 3a plus b, but we already know what a is, it's 1. So plus b equals 2x minus 5. Well, x is equal to 5, so that's 2 times 5, which is 10, minus 5, which is equal to 5. So b is simply equal to 5, and then this multiplies and becomes 3, and when we transpose it, it becomes negative. So 5 minus 3 is 2. And then a plus b plus c, but we know that a is 1, b is 2, and then say plus c equals, and it's equal to x, which we know is 5. So it's equal to 5, and so c is equal to 5, and then 1 plus 2 is 3. Transpose it, it's negative 3. So 5 minus 3 is equal to 2. So this is our formula. Our pattern's formula is Tn equals n squared plus 2n plus 2. Okay, so this is what it looks like. Now the question is specifically to prove that all the terms are going to be positive in this pattern. Okay, remember that this is a pattern, and because they're already calling it a pattern and we already know this is a pattern, we need to take into account that with a number pattern, you can only consider n values that are specifically natural numbers. So what I mean by this is you can't have a term number that is a fraction. Okay, there's no such thing as term or half or term -3/2. Okay, and term -2, for example. It's always numbers like 1 and 2 and 3 because these represent positions. Okay, we can have the second position, but we can't have the second position. Okay, so because of that, we should already consider that in this, we already know that n is an element of all natural numbers in this. Okay, so we'll just consider that already since this is a pattern. So how do we prove that this is always going to produce positive values if we know that n is an element of all natural numbers? Well, let's go ahead and look at each part of this expression. So we have n squared. N squared, regardless of what n is, even if n was not an element of natural numbers, even if it wasn't numbers like 1, 2, 3, and so on, it would still always be positive because you're squaring this value. So this will always be greater than 0 for where n is an element of all natural numbers. I'll just keep this since we know that n definitely is an element of all natural numbers because we're dealing with a pattern. And we also know that 2n is also going to be greater than 0 because now this is an element of natural numbers. You can only use natural numbers here, but you're just multiplying by 2. So it's also going to be greater than that. So this will conclude that the entire expression, n squared plus 2n plus 2, okay, you're just still adding to what is already positive. It will still maintain this. It will still be positive. It's always going to be positive for all values that are natural numbers and even real numbers, really. Okay, so this would be one of the main things because it is a pattern in the first place. Okay, so we could leave it like that. Okay, and that is it for this question. Moving on to the next question. Question 2.3 says, consider the geometric series, and we have this geometric series in terms of p for where p is not equal to 3. Okay, and you can see they said that because if p was equal to 3, you'd have 3 minus 3, which is 0. So you'll just have 0, 0 plus 0. Okay, so that's why. And they're specifically saying determine the values of p for which the series converges. So for a series to converge, the ratio will be greater than -1 but less than 1. So let's find that common ratio, that constant ratio. So we can find that by taking the next term divided by the previous term. Okay, it can be term 2 divided by term 1 or even term 3 divided by term 2. So if we say r is equal to, and we're going to just say term 2, which is 3 over 4 and then p minus 3 all squared divided by term 1, which is 1 over 2 and p minus 3, then what is this equal to? And it's going to be in terms of p. So let's just deal with this first. You see that you have p minus 3 all squared and then p minus 3. So one of it will cancel here and you're just left with p minus 3 here. And so what is 3 over 4 divided by 1 over 2? 3 divided by 1 is 3, 4 divided by 2 is 2. So it's 3 over 2. So we have 3 over 2 and then times p minus 3. We might as well just distribute here. So making this the ratio 3 over 2p, and then that's going to become -9 over 2. Okay, the values of p for which the series converge is where our ratio, which is 3 over 2p minus 9 over 2, is greater than -1 but less than 1. And let's just solve for this inequality. Okay, so with this inequality, in order to solve for p, we first need to get rid of this -9 over 2. So we can do that by adding -9 over 2 on all sides. Remember, these are really just two inequalities, okay? They've just been put as one since the values that it was pointing at were values that were greater than -1 but less than 1. You see that they fall within the same section, okay, within a common interval, really. So now that we have that, so we're just adding 9 over 2 on all sides. And so 1 minus 9 over 2, that's like saying 2 over 2 minus 9 over 2, which is negative 7 over 2. So this becomes negative 7 over 2. And then this stays 3 over 2p. And we're saying this is greater than negative 7 over 2, but less than. And we're saying 1 plus 9 over 2. Again, that's like saying 2 over 2 plus 9 over 2, which is 11 over 2. Okay, and now we just have to solve for p. So to solve for p, we need to get rid of the 3 over 2. So we can do that by dividing by 3 over 2 all through. So, or you could see this as multiplying by 2 over 3. So you can multiply by the reciprocal, because if you do that, it's going to help to cancel out that numerator and the denominator. So we can just see this as multiplying all sides by 2 over 3. Okay, so therefore p is greater than, and when we multiply here, negative 7 over 2 times 2 over 3, you see that the 2's will cancel diagonally and you're left with negative 7 over 3. And so p is greater than negative 7 over 3, but less than, and 11 over 2 times 2 over 3, those cancel and you're left with 11 over 3. And that is our answer. Okay, and also just remember that they did say for where p is not equal to 3. You see that 3 is also going to be included in one of these numbers that it's referring to. Okay, negative 7 over 3 and 11 over 3, when we look within that, you're going to get a 3. 3 could be represented as 9 over 3. Okay, it will be within that. So just ensure that you also tell them p is not equal to 3, like they told us. And that is our answer. Moving on to the next question. And then question 2.3.2 says, if the sum to infinity of the series is 1, okay, determine the value of p. So the sum to infinity is 1. Sum to infinity, the formula is a over 1 minus r. So we just need to find a, and then we already know what r is in terms of p, and we know that the sum to infinity is actually equal to 1. So what is a? A is the first term in our pattern, which is 1 over 2p minus 3. So we'll tell them 1 over 2p minus 3. And then r was that constant ratio. You see how we divided term 2 and then divided by term 1, right? So that is our ratio, and we'll just take it like that. And we'll substitute them. It's going to create an equation in terms of p. So our equation is going to be the sum to infinity, which is 1, is equal to a, which is, we might as well just distribute there. So that is a half p minus 3 over 2, that is a, over 1 minus r, which is 3 over 2p minus 9 over 2. Okay, and we're just solving for p. Okay, so to just remove this fraction, just multiply, cross multiply. This is a fraction, okay? It's something over something, so we're just going to cross multiply. These multiply to stay exactly the same, so they just stay 1 minus, and we have 3 over 2p minus 9 over 2. And then these multiply to also just stay a half p minus 3 over 2. So we could have also just used that as an opportunity to distribute here. So that's just going to be minus 3 over 2p plus 9 over 2. Okay, so now we're just simplifying. So this is 1 over 2p. And then if you transpose that, that is plus 3 over 2p is equal to, and we have 1 plus 9 over 2. So 1 can be 2 over 2. So that's 2 plus 9, which is 11 over 2. And now we can transpose this. So this is plus 3 over 2. So 1 over 2 plus 3 over 2, that gives us 2, because 4 over 2. So that's 2p is equal to, and then 11 plus 3 is 14. 14 divided by 2 is 7. And finally, when we divide both hand sides by 2, p is finally equal to 7 over 2. And that is our answer. Okay, and that is it for question 2. Question 3.1 says, if we have this series, okay, and it's a geometric series, as you can see, it is in the form of a times r raised to the power of n minus 1. Okay, so we can already see what the value of r is. And they're telling us that if the sum of this series with this formula is equal to 59,046, we need to determine the value of n. Okay, so this is for 5 marks. Let's just note down what this n is referring to. You see, there's a difference between this n, the number you end at, and the n, the number of terms in the series. So let's just point these out first. So n, right, the number that you end at here, because it starts at k equals 2, ending at n. So this is simply that number that will be up there. It's not the same as n, the total number of terms that we have. So here, this will be the terms. And this is how we find the total number of terms. We find it by saying that top number, so that n value that you end with, minus this value that we start with, k equals 2. So minus that value of 2 and then plus 1. That will give you the total number of terms. So let's keep this in mind when finding n, the number we end at. Okay, the k value we end at. Now, in order to find this, they told us the sum of the series. So we're going to use the sum. Okay, we can clearly see that r is equal to 3. And what is a? A is the first term. So we will find a as a result of substituting this first value, k equals 2, into this formula. So we'll say 2 times 3 raised to the power of 2 minus 1. And so that's going to be 2 minus 1 is 1, and then 2 times 3, which is 6. So we know now that a is equal to 6. Okay, so we have r, we have a, and we can find this. So we'll say Sn is equal to, so that is a multiplied by r raised to the power of n minus 1 all over r minus 1. Okay, so this is where r is greater than 1. Now, just note that this n that we have here, this specifically refers to the terms, okay, the number of terms. This is the number of terms, and we're just going to keep this in mind. So once we find this, we need to still tell them what exactly this n is, because this is n, the number you end at. Okay, so let's see. Let's substitute our values. Sn, the sum of the series, is 59,046. So we'll say 59,046 is equal to, a is 6, and we have, okay, so r, which is 3, raised to the power of n minus 1, all over r minus 1. So 3 minus 1. Okay, 3 minus 1 is already 2. So we just have everything else. 59,046 is equal to 6 multiplied by 3 to the power of n minus 1, and then over 2. Then we can just multiply both hand sides by 2 to remove that 2 in the denominator. So on this side, we'll have 6 multiplied by 3 to the power of n minus 1 is equal to, and what is 59,046 times 2? That gives us 11,800. Okay, so that's 118,092. Okay, so this is what we have. And now we can finally divide both hand sides of this equation by 6. So this is equal to 3 to the power of n minus 1 is equal to, and we'll take that value again and say divided by 6, and we get 19,682. Okay, is equal to, we can transpose the negative 1, so it's 19,683. And now we'll just add that 1 here so it reflects as well. So plus 1. And now we have this. Okay, we can go ahead and just make the bases the same. So let's see if the base can actually be made 3. So 19,683 is equal to, and I'll say shift fact. So it's 3 to the power of 9. Okay, so 3 to the power of n equals 3 to the power of 9. So therefore, this means that n is equal to 9. Notice that n that we are referring to here is the number of terms. The number of terms is equal to 9. Okay. Now we need to now apply that here because they're not asking for the number of terms. They're asking for n, the value we end at. So if the total number of terms are 9 terms and we started at k equals 2, then where are we ending? We have to have been ending at 10 because they should be a total of 9 terms, meaning k equals 2 is your first term, k equals 3 is your second term, and then 4, 5, all the way to 10, and that will give you a total of 9 terms. Okay, another way to have seen this is you could have just used this equation. The number of terms is equal to the number you end at minus 2 plus 1. So we could have said the number of terms was 9 is equal to the number you end at minus 2 plus 1. And so that is 9 equals n minus 1. And if you transpose the 1, it's 10. So n equals 10. The number we end at is 10. But this is specifically 9 terms in total that we have. And that is our answer. N is actually equal to 10. And that is it for the first question. Moving on to the next question. Now, question 3.2 says, an equilateral triangle RST, so RST, with sides of length 12p units is drawn. Then a second triangle is drawn by joining the midpoints of the sides of the first triangle, RST. Okay, so this is now drawn by taking the midpoints of each side. Remember how they said each side of the first triangle is 12p units. So they find the midpoint, and then that's where that point is going to be drawn. Find the midpoint of this 12p again, and then that's where that point is, and so on. And then they tell us that each triangle thereafter is drawn by joining the midpoints of the sides of the previous triangle as shown on the sketch, and this continues indefinitely. And the first question, 3.2.1, says, write down in terms of p the length of each side of the second triangle. So we're looking at this triangle over here. Okay, so what did they say about how this triangle has been drawn? It's drawn by finding the midpoints of each of the sides. So if we took this length, right, we can even look at it from this side. If we found the midpoint of this, right, then that would mean that this over here is 6p units, and then that's 6p units. And these are all equilateral triangles. So all the sides would have a length of 6p units for this triangle. And then it will also just be divided by 2 again, 3p units for this little triangle. So the second triangle, each of them will have a length of 6p units. And that is our answer in terms of p. Okay, moving on to the next question. Question 3.2.2 says, calculate in terms of p the perpendicular height of triangle RST. Okay, so the perpendicular height of this larger triangle. So it's really just this line that I've just drawn here. So from the highest down to the base, and it is of course perpendicular to that base. Okay, we can find this by looking at half of the triangle. So looking at this triangle over here. So if we have that triangle, we can see that the hypotenuse is 12p units, and the side, okay, the base of this triangle would be half of this, okay, half of that 12p, so that's 6p. Okay, so we can just use Pythagoras to find this. So we're trying to find this length, okay, that perpendicular height. Let's just go ahead and call that h, that's fine. So we can just say that to find this height, we'll say h squared is equal to, now we need to take the hypotenuse squared. So this side, meaning 12p all squared. So 12p all squared minus, and then the other shorter side, 6p all squared. And let's see. Okay, so h squared is equal to 144p squared minus 36p squared. Okay, and 144 minus 36. So we have h squared equals 108p squared. And then we need to still square root both hand sides because we're trying to find out what that perpendicular height is. It's a height, it's a length. So we don't have to consider negative here. So h is equal to the square root of 108p squared. That's going to be a third. So let's just say square root 108 is, as a third, it's 6 square root 3. So that is 6 root 3p. And that is our perpendicular height. Okay, so that is it for that question. Moving on to the next question. Question 3.2.3 says, show that the sum of the areas of the triangles formed will not exceed 48 square root 3p squared. Okay, so you see how they're saying that we need to show them that it's not going to exceed this. It's because if it's not going to exceed a specific amount, remember these are areas, right? You're adding. So if it doesn't go beyond a particular amount, it just means that the series is going to converge because each term in the series, all these areas, they're going to head towards a specific value. Okay, so that's why it's not going to exceed a particular amount. And we would have already known that it's going to converge from the beginning, where they said that the next triangle is drawn by joining the midpoints, okay, of the sides of the other triangles. So because that length became half of the other one becomes half of the other one, and they just keep being halved, it's going to converge. Okay, but regardless, we're looking at the areas, the sum of the areas. Because we know that these values are going to converge, we're really finding the sum to infinity. Okay, so let's go ahead and find the sum to infinity. But remember that to find the sum to infinity, you need certain things. First, you need the value of a, and then you need the value of r. Now, this question is for 5 marks. So first, let's go ahead and expand these areas. So we're going to write down the pattern for the areas. So the first triangle will look like this. Triangle 1. This is going to be, the area of this triangle is going to be found by saying a half times the base times the height. Now, in the first triangle, we can see that the base is 12p units and the height, we already found it. Also note that with the height of this triangle, right, and the heights of the other triangles, if the height of this first triangle was, we had it being 6 square root 3p units, so that means that the next triangle will be half of this. And then the next triangle will be half of whatever the previous height was, and so on. So this is going to be a half multiplied by our base of 12p units multiplied by our height of 6 square root 3p. Okay, so that's how we find the first triangle's area. Okay, so the area of triangle 1 is going to be, so a half times 12p, that's 6p. So we're going to have 36 square root 3p squared. That is the first one. And then the second triangle, triangle 2. Okay, so to find the area, we'll just say a half multiplied by, and the base of this was half of that. So remember, it was 6p, and then multiply by, the height is going to be half of this. If you say 6 square root 3 divided by 2, okay, of course it's p, it's going to be 3 square root 3p. Okay, so that's what the height is here, 3 root 3p. And so the area is finally equal to 6 times a half is 3. So 3p times this is going to be 9 square root 3p squared. And then the next area, the area of the third triangle. Okay, so really we just need 2 triangles because we just need the ratio. But okay, the third triangle will look like this. Okay, let's just get 3 terms. So a half multiplied by, so the previous triangle's height was 3 root 3. So we will divide that by 2. So that is just 3 root 3 over 2p. And then when we multiply them, they give us, so we'll have a denominator of 4. And the numerator is just 1 times 3 times 3. So that's 9. So 9 square root 3 over 4p squared. And so these are the areas of each of our triangles. Okay, so we're really just trying to find the sum to infinity. So the value of a here, the first term, is 36 root 3p squared. The value of r is, we'll just take the second term divided by the first. So if we take 9 root 3p squared divided by 36 root 3p squared, then this means that they will cancel and you have 9 divided by 36. Okay, so let's just cancel. These two will cancel. The square root 3's are gone. And so just 9 over 36. Okay, 9 is a factor of 36. So it's going to be 1 over, and 36 divided by 9 is 4. Okay, so that's the ratio. And now we can just show them that the sum to infinity is not going to go beyond this value they told us. So sum to infinity equals a over 1 minus r. So the sum to infinity is equal to, a is this, we'll take that just as it is, and then divided by 1 minus r. Okay, so this goes over 1 minus a quarter. So that's what we have. And let's just simplify this. So this is just 36 square root 3 p squared. And we're dividing by 1 minus a quarter is 3 over 4. And so it's really just multiply by 4 over 3 if you're using tip and times. Okay, so that means that we have common factors here. This is what we can do. We can put this over 1 so that now we're multiplying these two fractions together. So you can look across for anything that is common. You see that 3 and 36 have 3 in common. So 36 divided by 3, that gives us 12. And then we still have the square root 3 p squared. And here when we say 3 divided by 3, that just gives us 1. So that's gone. So this became 12 and that just became 1. And then we're saying multiply by 4. Okay, so yeah, it actually ends up being 48 square root 3 p squared. That's what the sum to infinity is. And so we can see that, yes, it really does not exceed 48 square root 3 p squared. So we can finally just conclude that. Okay, so the sum of the areas of all the triangles formed, okay, the infinite triangles, is 48 square root 3 p squared. Therefore, it will not exceed this value. And that is our answer, and that is it for question 3. Question 4 says the graphs of f of x, which is equal to ax squared plus bx plus 15 over 2, and g of x, okay, which is another parabola that we have, but it's concave up, and that is x squared plus 2x. So we have the full equation of that. And these are sketched below. A and B are the x-intercepts of f, and we have D, which is P, and 8, and that is the turning point of the graph of f. C is the x-intercept of the graph of G, and the graph of G passes through the origin as well. So that is an x and a y-intercept that we have there. E is the turning point of the graph of G. And as you can see, they're vertically in line with each other. So you can tell which coordinate they share, whether that's the x or the y value. And the first question, 4.1, says, write down the coordinates of f. So what is f? Where is f? F is on the y-axis. So it's the y-intercept of this graph, okay? And we can see that is the graph of f. So it's the y-intercept, and the graph of f has been given in its standard form. So the y-intercept is that constant value without any variable, without an x. So that is 15 over 2, and we can tell them that f is that y-intercept 0 and 15 over 2. Moving on to the next question. Question 4.2 says, determine the coordinates of C. So C is a point that is on the graph of G, and it's specifically on the x-axis. So it's the x-intercept of this. So we already have the full equation of G, so we can just make y equal to 0 to find the x-intercept. So that is g of x, which is going to be 0, equals x squared plus 2x. And then factorize this. It's two terms, but we have a common factor of x, so we'll take that out. What is left in the first term? X. And in the second term, it's positive 2. Therefore, x is either equal to 0 or x is equal to negative 2. We can see the one that is 0. It's at the origin. Okay, so this is the one that gets negative 2. So there we go. C is simply just the coordinates, negative 2 and 0. And that is our answer. Moving on to the next question. Question 4.3 says, the turning points of the graphs of f and g lie on the same vertical line DE, like we saw. Determine 4.3.1 the value of p. Okay, so they lie on the same vertical line. But remember that g is complete. We have the full equation of g. So we can use g to find out exactly what p is. So we're trying to find the x value of the turning point of g. So g of x is equal to x squared plus 2x. And to find the turning point, you can either use this equation negative b over 2a, and that will find the x value, or you could also just derive this and then set it equal to 0, make the gradient equal to 0. I'll just go ahead and use this method. So negative b over 2a, meaning we're saying negative, and the value of b here, this is bx, is 2. So negative 2 over 2 times a, which is an invisible 1 there. So this is just negative 2 over 2. So therefore, x is equal to negative 1. And that's the value of p. So we could have already just initially said this is p. And that is our answer. P is equal to negative 1. Moving on to the next question. Then question 4.3.2 says we need to determine the length of DE. Okay, so DE. We just found P to be negative 1. And this lies on the same vertical line. So it means that its coordinates are also negative 1 and then some y value. So if we find out what exactly that y value is, we'd be able to take this point's y value, which is 8, and just say 8 minus whatever that y value is, and that will give us the length of DE, since DE is a vertical line. So we simply just need to find that y value of this point E. So E lies on the graph of G, and we have the full equation, and we also know the x value is negative 1. So let's go ahead and substitute negative 1 into G. So we're saying G, negative 1 is equal to, and this is going to be negative 1 all squared plus 2 times negative 1. So that's going to be negative 2. 1 minus 2 is negative 1. So it's also negative 1. Okay, so the y value of point E is negative 1. We just found that. So if this is negative 1, you're just saying to find DE, we'll say 8, that y value of 8 minus the y value of negative 1. So DE finally is equal to 8 minus negative 1, which is equal to 9. And that is our answer. DE is equal to 9 units. Moving on to the next question. Question 4.4 says, show that A is equal to negative 1 over 2 and B equals negative 1. Okay, so they're referring to the values of A and B in the graph of F. Okay, what about the graph of F do we have? We have this, right? We have this point. We have the full point now. So, but it's specifically a turning point. And a turning point is very useful because it can be used in two ways when you're looking at the equation of this graph. So let's go ahead and take this point D, the turning point of F, and the graph of F, and just rewrite this down first. Okay, and here's how we can use this. You see that we have two things missing, meaning you can form two equations to solve for A and B. And we're going to use this turning point in two ways. So the first way we can use this is as a turning point. So if you're using it as a turning point, this is how it's going to work. Okay, so at the turning point, we know that this is a concave down parabola first of all. And we know now that at the turning point, this is the point where the gradient of this graph is equal to 0. Okay, the gradient is increasing all through here. That's why the graph is moving upwards, and then decreasing all through here. But at this particular point, at the turning point, it's stationary. So the gradient is equal to 0. And we're going to use that fact. So we'll find the gradient of f by deriving it. So f prime of x is equal to coefficient times exponents, that's 2a. And then exponent minus 1 is 1, but you don't have to rewrite that. And then coefficient times exponent is positive b. And we have the x exponent minus 1. There was already a 1, so minus 1 is 0. Anything to the power of 0 is 1, and b times 1 is still b. Now, what we're saying here is, in this graph, the gradient is equal to 0. But specifically, it's the gradient at the point where x is equal to negative 1. That is the turning point. So we'll say, at f prime of negative 1, we know that the gradient is equal to 0. So in place of x, substitute negative 1, but in place of the gradient, substitute 0. So this is going to be 2a times negative 1, and then plus b is equal to 0. And now you can just make b the subject, since it looks simpler to make a subject. 2a times negative 1 is negative 2a, and if you transpose that, it's positive 2a. Okay, so we've got our first equation, and it's b is the subject. And now the second way that we can use this point D is as an actual point on the graph. So we used it first as a turning point, now as a normal point on the graph. So we would use the actual graph of f. But in place of x, we'll substitute negative 1. And in place of y, we'll substitute 8. So we're saying f of negative 1 equals a times negative 1 all squared plus b times negative 1 plus 15 over 2. And then the y value that goes with this is 8. So 8 is equal to negative 1 all squared is 1, times 1 is a, and then b times negative 1 is negative b, plus 15 over 2. And then we can just make negative b the subject of this equation. So take it over, transpose it, and now we have a, and it's positive 15 over 2 minus 8. 8 can be written as 16 over 2. 15 minus 16 is negative 1, so that is just minus a half. We can simply just say that b is equal to b and then equate. So we're saying 2a equals a minus a half, and then transpose the a. 2a minus a is equal to negative a half. So there we go. We found out that a is really negative a half. And to find b, just substitute this value of a in one of the equations of b. This is easier to use. So b equals 2 times negative a half. And you see that diagonally, those 2's will cancel. Therefore, b is simply equal to negative 1. And that is our answer. So a really is equal to negative a half, and b is equal to negative 1, like they said. Moving on to the next question. Question 4.5 says, determine the equation of a straight line joining the points of intersection of the graphs of f and g. Round off your answer to 2 decimal places. Okay, we're finding the equation of a straight line, so not really sure why we have to round off to 2 decimal places, but maybe with these intersections, right? Maybe they create a horizontal line that is a fraction, and then they want us to just round off to 2 decimal places with that equation. Okay, so we're just trying to find out the equation of the line joining these 2 points together. That's it. Okay, so in order to do that, it's just a straight line. You're just trying to find the equation of a straight line, and the 2 points that are on this line are the points of intersection. So we just need those 2 points of intersection. We can find that by equating both equations, okay? Because the point of intersection is the point where the x and the y value of the both graphs are exactly the same. So let's rewrite our graphs. First, the full equations, knowing what a and b are now. Okay, so f of x is now equal to, because a is negative a half, it's negative a half x squared, then minus 1, which is negative x, and then that was 15 over 2 that we had there. Okay, so then plus 15 over 2, and then we rewrite g that we have. Okay, so now we can go ahead and equate these. So we'll say f of x is equal to g of x, and this will solve for x. It will tell us the x values at which they are exactly the same. Okay, so I'm just going to put the g of x first. We'll leave it as g of x just because I want to keep the positives on the left-hand side. So x squared plus 2x is equal to negative a half x squared minus x plus 15 over 2. And so this is now going to be x squared plus 1 over 2 x squared plus 2x plus x. And then that comes over and becomes negative 15 over 2 is equal to 0. Okay, so we have a trinomial. So when adding these two together, 1 plus a half is 3 over 2 x squared. And then we have plus 3x and minus 15 over 2 equals 0. Okay, you could use the quadratic formula to find this. Okay, so x is equal to, and I'll put down the quadratic formula. Okay, so x is equal to, and we'll say negative b, and that is just going to be, the b value is 3. So plus minus the square root of 3 squared, so just 3 squared minus 4 times a, which is 3 over 2, times c, which is negative 15 over 2, and then all over 2a. So 2 times 3 over 2. And let's get our first x value. Okay, and this is what we get for the first one. It's square root of 6 minus 1. But as 2 decimals, which I don't want to really round off yet because this is not really just the equation yet. We still have to see what that will look like. So that is 1 point. Let's leave it at 4.5 for now, but I'm still going to use that. That's why I'll leave that there. Or x is equal to, and we'll change that to a negative. And we have negative 3.45, but as a third, it is negative square root 6 minus 1. So x is equal to negative 3.45. Okay. Okay, so now we need those y values so we can find the equation. Okay, so the y value that goes with that. And we're going to take these x values and substitute it into either one of the equations. Now, you see that g is much easier to use. So let's go ahead and use g and find out what the y value will be for these 2 points. Okay, so g of, instead of saying 1.45, let's just say root 6 minus 1 so we can get an exact value. Okay, so that is root 6 minus 1 all squared minus 2 times root 6 minus 1. Okay, so let's put that on the calculator and just see what we get there. Okay, and when we substitute the first value, we get 5. Okay, so this first x value gives us 5. Okay, so this is equal to 5. And let's substitute the second one. So that one was where we had negative root 6 and then minus 1. And let's see what that gives us. So we can find the y value to find this graph's equation. So this is minus, and then that's minus now in those ones. Okay, it also gives us 5. So here's the thing about this. 2 different x values giving you the same y value. So it means, yes, here we had negative root 6 minus 1. And here we had positive root 6 minus 1. But they gave the same y value of 5. This means that this is a horizontal line. And so the equation of a horizontal line is always going to start as y is equal to whatever number on the y-axis it passes. So because it passes 5, the y values for these points are 5, it's just y is equal to 5. And that would be the equation of that line. Okay, now in this case, I didn't really fully respect the rules because they did say round off to 2 decimal places. So at this point, I should have just used that rounded off answer. Let me just see how far it would be if I replace this with 1.45. Okay, as you can see, not that far. Okay, if you use 1.45, which you probably should, so you just show them that I substituted this value in. Okay, and of course, you would also do this for the other one. So just show them that you did actually find these x values. Okay, so we could change that to negative 3.45. Okay, they gave the same answer, of course, because they gave the same answer initially as I said as well. So we can just tell them that the equation of this horizontal line is simply y is equal to 5.00. And that is our answer. And that is it for question 4. Question 5 says, the graph of f of x is equal to log x base a is sketched below. And we have a point q, which is 1 over 4, and 2 is a point on the graph of f, and p is the point of intersection of the graph of f and the x-axis. Okay, so that is the x-intercept of this log graph. Question 5.1.1 says, determine the value of a. Okay, so we have the graph and we have 1 point on this graph, so we can substitute it in place of x and y, and that will help us to find that value of a. Okay, so f of x is equal to, we have log x to the base a, and then we're going to substitute this point in place of x and y. So 1 over 4 and 2, let's see, 1 over 4 and 2, so this is x and this is y. Okay, so f of x is 2. So we're saying 2 is equal to log and base a, and then the x value is 1 over 4. And now to solve for a, we can just put this in exponential format. So a raised to the power of, this is the exponent, okay? So 2 is equal to, and this is the value the exponent is equal to. Now to solve for a, it is a quadratic equation, so we can get rid of that squared by square root in both hand sides. Of course, this means we have to consider the positive and negative solution. But this is an exponential function, so it's going to be positive. The square root of 1 over 4 is 1 over 2. It can't be negative because if it's negative, you're going to get a graph that will alternate between positive and negative values when raised to that exponent. 1 will be positive depending on whether you raised it to a even or odd number. For example, negative 1 over 2 raised to the power of 2 would give you a positive value, but negative 1 over 2 raised to the power of 3, that will be a negative. Okay, so that does not form an exponential function. Okay, so a is equal to 1 over 2, and that is our answer. Moving on to the next question. Question 5.1.2 says, determine the inverse of graph f and write your answer as y equals. Okay, so the graph of f right now, let's just rewrite it as y equals, and we have log, and the base is 1 over 2. Okay, and now we just need to swap x and y. So x is equal to log, and now we still have the base of 1 over 2. Now this is y. And now make y the subject. To make y the subject, just put this back in exponential form because this is the answer to your exponential expression. So our base is 1 over 2. We'll just say 1 over 2, and then it's raised to the power of the exponent, okay, in the log function. That is always the subject of our equation. So raised to the power of x, and then the answer is y. So there we go. It is y equals 1 over 2 raised to the power of x, and that is the equation of the inverse. Moving on to the next question. The next question says, sketch the graph of the inverse showing intercepts with the axes and at least one other point on the graph. So they want to see that intercept and at least one other point. So the point they're referring to is probably this point that they've already put down here. So the other point that we have is this point, the x-intercept of our log function. So if it is an x-intercept in the graph of f, then it's going to be a y-intercept in the inverse. So we can just go ahead and find this first. Let's find p. Okay, so find p in your exponential function. So we can see that it's an x-intercept in the log graph. So in the inverse, the exponential function, it's going to be a y-intercept. So to find a y-intercept, you simply make x equal to 0. So this is going to be y equals, and that is raised to the power of 0. So anything to the power of 0 is 1. So now we know that p, okay, or p prime really, on the exponential function, not the log graph, this is going to be 0 and 1. Okay, now we can go ahead and sketch our graph. So our graph, let's just plan it out here. You can see from the way this graph looks, okay, on the positive part of the y-axis, it's closer to that y-axis. So it means that if you were reading it from the negative part of the y-axis moving to the positives, then you can see how it's actually just shooting down, moving closer and closer to, you'd have to look at it looking at it this way. So if you looked at it looking at it this way, tilting your head this way, then you can see that it's moving closer and closer to that y-axis. Now the inverse is going to do exactly what this graph is doing, but it's going to do that on the other axis. So instead of on the y-axis, it's going to do this on the x-axis. So you see that this is the positive part of the y-axis. Here's the positive part of the x-axis. This graph is going to be close. Okay, it's going to come from being really close to that x-axis. And then you see towards the negative part of the y-axis that this graph is shooting away from that y-axis. So that's what it's going to do on the negative part of the x-axis. So it's going to do this. And then you're going to have that y-intercept, okay, of 0 and 1, and you're going to have that other point. Now the other point, since we have a point on the log graph, 1 over 4 and 2, this point on the inverse is just going to switch the x and y values. So it's going to be 2 and 1 over 4, okay? So 2 and 1 over 4 would probably be somewhere here. Okay, so that is just an example of what it's going to look like. And now we can draw that graph down. Okay, so you can always just plan it out looking at the original graph, and then you'll be able to see what the inverse would look like. So here are our axes, and we must just make sure to point out those 2 points. So our inverse is going to look like this. It's going to just shoot down and move closer and closer to that x-axis. Okay, where we'll have P being the y-intercept, okay, P prime, and that is 0 and 1. And then the other point we have is Q prime, which is just on the inverse. So it's going to be, instead of it being, that one was 1 over 4 and 2. So it's going to be 2 and 1 over 4. Okay, so you can make it a little lower than this just because of how it is compared to this. This one is 1. This one has a y value of 1 over 4. Okay, so that's what our graph would look like. And we can just say that is H. Okay, they didn't say anything about asymptotes, so we can just leave it like this. And that is our graph. moving on to the next question. The last question, 5.3, says determine the values of x for which f of x is greater than negative 5. Okay, so this is referring to this original log graph that we have. So to find out where it's greater than negative 5, we need to first find out where it's equal to negative 5. So negative 5 as a y value, let's say it was somewhere here. Okay, we need an actual point where we can line this up to a point on the graph. So negative 5. And so they want to find out where this graph is going to be greater than negative 5. So once we find out what exactly that x value is, where it's equal to negative 5, we can just say, okay, it's greater than negative 5 for all these values where, so we can just say it's greater than negative 5 all through here. Okay, because all of these will have y values greater than negative 5. If you take any point and you line it to the y-axis, it will be greater than negative 5. So everything above there. Okay, but there's one more thing you need to note. You need to remember that over here, because this is a log function and we saw what the exponential graph looked like. It looked like this, right? This actually has an asymptote. Notice how this graph moves closer and closer to the x-axis, but it will never pass the x-axis, okay? Because as it is written, y equals, and we have that value of a raised to the power of x, okay? We don't have any plus q here, so it means that the value of q is actually 0. So we have a horizontal asymptote of 0, of x equals 0, right, on the exponential function. But this asymptote on the log graph will not be a horizontal line. It will be a vertical line. Okay, see, if the original function has a vertical asymptote, the inverse will have a horizontal asymptote. And that's how it works. So this has a vertical asymptote of, and it's vertical, so it will start with x is equal to 0. So it's never going to pass 0. Okay, so first things first, we need to find out exactly what this x value is. What is the x value of the log graph at y equals negative 5? Okay, so let's take our graph and we're trying to find out where this is greater than negative 5. Or you can just find out where it is equal to negative 5 first. Okay, so to find out where it's equal to negative 5, let's put it back in exponential format so we can solve for x. Okay, so the base is 1 over 2. It's raised to the power of this as an exponent, okay? Because the answer is your exponent. So negative 5, and then it's equal to x. So that will tell us x. Okay, so that means x is equal to, if you raise that to the power of 5, it's going to be 32. So this is actually going to be, what happens is both the numerator and denominator, they're going to be raised to the power of negative 5 because they have an invisible 1 as the exponents. So that 1 times negative 5 is negative 5, and that's 2 to the power of negative 5. But because the exponents are negative, you would move them from where they are. So we move that to the numerator and becomes 2 to the power of positive 5, and that becomes 1 to the power of positive 5. 1 to the power of 5 is still just 1. And so that is 2 to the power of 5, which is 32. So x is equal to 32. That is where it will have a y value of negative 5. Okay, so looking at our graph, this is at 32. And now the values of x for which this shaded region exists would be, remember, it can't go past 0, okay, because it's just going to get closer and closer to that y-axis. So look at these values. You see where they are relative to 32 and even 0. These are values that are greater than 0, but less than 32. And that is our answer. So finally just tell them that this means that x is greater than 0, but less than 32. And that is our answer. Okay, and that is it for question 5. Question 6 says, the sketch below shows the graphs of f of x is equal to a over x plus p plus q, and that is our hyperbola we have here, and g of x, which is a straight line. Okay, and this is decreasing. So k is missing here. The graph f of x cuts the x-axis at a, which is negative 8 and 0. So let's just point that out. It cuts the x-axis here at negative 8 and 0 and cuts the y-axis at b. Okay, the asymptotes of the graph of f intersect point D, which is negative 4 and negative 1. Graph G passes the point D, meets the graph f at points C and E, and then cuts the y-axis at point F. Okay, and the first question, 6.1.1, says we need to determine the value of k. So that y-intercept of the graph of G. So looking at the graph of G, as you can see, we don't actually have a y-intercept over there, but we can still find this if we knew one point. Okay, we'll put it in place of y, again, y value and an x value, and it will help to solve for k. So the graph of G, as we can see, it actually does have one point. It passes this point, negative 4 and negative 1. So that's what we're going to substitute. We can go ahead and say that g of x equals negative x plus k. And then in place of x and y, we're substituting this point, negative 4 and negative 1 as x and y. So that means negative 1 is equal to negative, and we'll say negative 4 and then plus k. Okay, so this becomes positive 4, but when we transpose it, it becomes negative. So that's negative 1 minus 4, which is negative 5. So that means k is equal to negative 5. And moving on to the next question. The next question, 6.1.2, says determine the values of A, P, and Q. So they really just want us to find this equation, f of x. So let's find that. Let's see what we have. Do you see that they told us about this point of intersection of the asymptotes of the graph of f? So if the asymptotes intersect at negative 4 and negative 1, all that means is this x value over here is negative 4. Okay, so that's negative 4, meaning this vertical asymptote passes the x value of negative 4 on the x-axis. So its equation is x equals negative 4. And then the y value is negative 1, meaning that y value over there, that's negative 1. And so this equation is y equals negative 1. So what that means for our graph is this. You see how they've written it? This is not been written in the way the standard form of the hyperbola looks. It's supposed to look like this. Y equals a over x minus p plus q. Okay, so the plus q is fine. Whatever q is, that's what q gets. But with the minus p, we need to figure that out. So this is our minus p. We'll speak about what that is, and then we'll find out what the p they're referring to is. Okay, so these values, the vertical asymptote, that's what gets the p, okay, in the standard form of our equation like that. So this is negative 4, and q is negative 1. And so when we substitute it into our equation, into the standard form, the general form of the hyperbola, it becomes y is equal to a over x minus, now that was a negative 4, so minus negative 4, and then minus 1. So you see how this will become x plus 4. So in their equation where they say a over x plus p, the p they are referring to is this 4. Okay, so we need to ensure that it actually does look like the equation. So p in our answer will tell them that the value of p that they were referring to is positive 4, and we saw that q stays exactly the same, so that's negative 1. Okay, great. We found p and q, and now we can use this to find a. So let's complete our equation. Our equation, f of x, now looks like this. So f of x is equal to, a is still a, over, and now this is x plus 4 minus 1. Now you see at this point, only a is missing, meaning we just need to find some point on this graph, substitute it in place of y and x, and that will help to solve for a. Okay, so let's look at this. Do we have a point on the hyperbola? Yes, the hyperbola has this point over here, negative 8. Okay, and doesn't really have any other visible point, but it has negative 8 and 0. So we'll substitute that as the x-intercept that it is. So we're putting in a, negative 8 and 0 in place of x and y. So it means that 0 is equal to, we have a over negative 8 plus 4 minus 1. And now to solve for a, you see that we can just transpose this negative 1 so it becomes positive, and we have a over 4 minus 8 is negative 4. And so to solve for a, we just need to get rid of this negative 4 in the denominator so we can multiply both hand sides of this equation by negative 4. And so therefore, a is finally equal to negative 4. So there, we've solved for P, Q, and A, and that is our answer. Moving on to the next question. Question 6.2 says, determine the values of x for which f of x is greater than or equal to g of x. Okay, so do you see that it's greater than, but it's also equal to? So what we could find out first is where f of x is equal to g of x. Now we know that f of x equation looks like this because we found a. It is negative 4 over x plus 4 minus 1 is equal to, and g of x, that was negative x, and we found k to be negative 5. So we know now it's negative x minus 5. So it's equal to negative x minus 5. And let's just go ahead and solve for x. So we'll find out where they are equal, where they intersect first. Okay, so this is equal to, we're going to go ahead and transpose this. So bring it over, and now we have negative 4 over x plus 4 is equal to, and this is negative x. Now we have minus 5 over here. When this comes over, it becomes a positive 1. So that's minus 4. Okay, so at this point, we can cross multiply. So if you put this over 1, it's now a fraction, and we can cross multiply. So this multiplied by that numerator. So we will have x plus 4, and then multiply by negative x minus 4. We can actually take out a common factor here. So if you take out a common factor from this bracket, we'll have it outside here. And so what is left in here? You can look at it here. If you say negative x divided by that negative 1, okay, is going to be x. Negative 4 divided by that invisible negative 1 is positive 4. Okay, great. These are exactly the same. And so then here, negative 4 times 1, that gives us negative 4. And we have negative on both hand sides of the equation. So you can choose to divide or multiply both hand sides by negative 1 just to get rid of that negative. And so what we have here is, you see how these are exactly the same and they're being multiplied. Just like if you have x times x, it gives you x squared. So this is going to be x plus 4 all squared is equal to, and that becomes positive 4. And now we can solve for x by square rooting both hand sides. So to get rid of this squared, we'll say square root and square root, but you see that we are working with a square. So the positive and negative solution has to be considered. Okay, so now that we have this, we can say, therefore, x plus 4 equals, and in front of this, okay, because you need to consider the positive or the negative solution, we'll say this is positive or negative. And so the square root of 4 is 2, so it's positive or negative 2. And now we can finally solve for x here. X is finally equal to, transpose the 4, it becomes negative, and we have plus minus 2, meaning we're saying that x is either equal to negative 4 plus 2, or x is equal to negative 4 minus 2. So x is equal to negative 2, or x is equal to negative 6. Okay, so let's see where these points of intersection are. We're trying to find out where f of x is greater than or equal to g of x. So if it is greater than or equal to g of x, the places where they are equal would be where their x and the y values are exactly the same, meaning their points of intersection. You see how the graphs intersect at this point, and they also intersect at this point, okay, g and f. Now we need to find out where f is greater than g of x. This would be places where the graph of f has greater y values than the graph of g. And an easy way to see this is to use a vertical line or your ruler, okay, because it needs to be greater than g of x, okay, greater or equal to, but for the same x values. So I'm going to take this and I'm going to move across just to see where this will work. Okay, so looking at this over here, that particular x value, do you see that the graph of g has a higher y value than the graph of f. The graph of f's y value is over here. It's a negative value. Okay, graph of g has a positive y value. So it doesn't work over there because there the graph of g is greater than the graph of f. We need f to be above g. Okay, let's just keep moving and see what we have. Okay, when we get to this point, this is where they're equal. Okay, and now we know where they are equal. That's why we found the points of intersection. It was -2 and -6. And so what that means is these are their points of intersection. And we'll know that this is the -6 because it's further to the left. And this one is the -2. Okay, so we know those points of intersection now. And we're just trying to find out where f is above g. When we get to this point, they are equal. Great, that's going to be included. And now when you go more to the right, okay, after that point, you see that the graph of f has a higher y value than the graph of g. Okay, the graph of g's y value here is 0. And then the graph of f has a positive y value. And as we keep moving to the right, the graph of f has a higher y value than the graph of g. Okay, the graph of f is above g. So it means that it's working all through here, but then we get to an asymptote. So we're not going to take that. We're just going to stop there. And so it means that this is working all through here. Okay, so from -6, and then it's like that. Value is greater than -6, but less than -4 because it doesn't go beyond -4. Okay, let's see what happens after -4. After -4, you see that the graph of g is above the graph of f. That's not what we're looking for. F must be above g. Okay, it's still above, and then now they're equal to. Then when we go to the right of that point, -2, okay, you see that the graph of f is now above the graph of g. So it has a greater y value than the graph of g. And it keeps having a greater y value than the graph of g all through. It's always above the graph of g after that. So it also works here as well. And now we just have to tell them the x values for which these points exist. Okay, if we zoom in and just look at it, if you line this down to the x-axis, in this section over here, you see that it works all through here from -6 all the way to values that are less than -4, not equal to -4 because we have an asymptote here. So the inequality there is going to be x is greater than or equal to -6, but less than -4. Okay, so you see how that looks. And then for this part, okay, if you line all of these points up to the x-axis, you see where they are compared to this critical value of -2. These are values that are going to the right-hand side of -2, meaning they are values that are x is greater than or equal to -2. Okay, so it's going that way. So that would be our answer. We would finally just tell them that our answers here are x is greater than or equal to -6, but less than -4, or x is greater than or equal to -2. And that is our answer. Moving on to the next question. Question 6.3 says, a graph represented by h of x is equal to x plus t is drawn on the same set of axes as f and g. For which values of t will graph h be a tangent to the graph of f? Okay, so let's see. For which values of t will it be a tangent to the graph of f? Here is how we can look at this. Just remember what the graph of f looks like, because there's no use of using this same graph again. We know that it lies in the second and the fourth quadrant. So our graph looks like this. Okay, we have the graph of f, which looks like this. And now we're just going to tell them the values of t for which this new graph called h of x equals x plus t will be a tangent. Okay, now its gradient is 1. Okay, y equals mx plus c. We can see that the coefficient of x is 1. So it means that that graph is going to look like this. Okay, like that y equals x graph. But now t has to still be determined. So for it to be a tangent to the graph of f, here's how it could be a tangent. It could be a tangent in two ways. Okay, it could be a tangent if it touches, okay, this graph of f in the second quadrant once. So like that. It could be a tangent like that. It could also be a tangent like this to the other wing. Okay, so there's two possibilities, and it will still maintain that gradient that it has of 1. So how can we actually find out the value of t for which it will be a tangent? Well, what happens when it's a tangent? It intersects the graph of f. That's what it's doing. So we can make f of x equal to h of x and then find out the values of t for which this graph is going to intersect the graph of f once. And we can do that by manipulating the discriminant. So we will have the discriminant because with a hyperbola, we can make that a quadratic just because it has a denominator with x in it. So once you multiply by x, okay, and it's also being equated to a linear graph, okay, with x. Once you multiply by x, it's going to become quadratic. And so that's what we're going to use here. And f of x, remember, was negative 4 over x plus 4 minus 1 is equal to, and h of x is x plus t. Okay, so at this point, you see we still have this hyperbola. We're going to have to get the x plus 4 out of the denominator because with a quadratic equation, you don't have x in the denominator. So let's go ahead and do that by multiplying both hand sides of this equation by x plus 4. So multiply by x plus 4. But on this side, when multiplied by x plus 4, we're going to multiply by this as if it is one term. So it's multiplying to this term first. And so the numerator and denominator cancel, and we're left with negative 4. And then x plus 4 multiplied by negative 1. And you see that it's multiplying to one term. So x times negative 1 gives us negative x. And 4 times negative 1 is negative 4 is equal to, and then these will distribute. So x times x is x squared, and then x times 4 is positive 4x, then that is positive tx, and then positive 4t. Okay, so x squared is already positive on this side, so we might as well transpose these over to the right hand side. So 0 equals, and we have x squared, and this is plus 4x. Now, when this comes over, it becomes plus x. So together, they give us positive 5x. And I'm going to just keep this tx close to this one since they're both in terms of x. And then we have positive 4t. Now, negative 4 minus 4 is negative 8. When negative 8 comes over, it becomes positive 8. And this is what we have. Now, it is a quadratic equation. It's just we have t's here. You see, with this one, you have 5x and tx. They're both in terms of x. So they will both form the coefficient of x. And so we can just rewrite it like this. 0 equals x squared, and it's like taking x out as a common factor. So what are we left with here? In the first term, if you take x out, you'll be left with the positive 5. And then if you take x out, you're left with the positive t. So this is what we have, okay? And then lastly, our constant is just plus 4t plus 8. And that is the constant because it's the only one without x, okay, that variable. So this is what we have, and it is in the form of ax squared plus bx plus c equals 0. Okay, a being 1, and we have b is the coefficient of x, which is 5 plus t, and then c is everything without the x, which is the 4t plus 8. So now we can use the discriminant. We're going to ensure that for this quadratic equation, the discriminant will have one root, okay? We want to find out the values of t for which it will be a tangent to the graph of h. So it intersects, okay, at one place. We don't want it to intersect like that, okay, by having 2 points of intersection. So this is how we're going to do this. We're going to say, let the discriminant, delta, be equal to 0. So if you make the discriminant equal to 0, that's how you get equal roots. And what they mean by equal roots is roots that could look like this. Okay, so the factors would be maybe something like x minus 1 times x minus 1 equals 0. You see how these are the exact same thing? So they're equal roots, and when you solve for x, you're really just saying that the root is equal to 1. So it has one root, and that's what we're trying to do here. So we're going to make the discriminant equal to 0, and so we're saying the discriminant is found by saying b squared minus 4ac is equal to 0. Okay, set it equal to 0. So what is b? B is 5 plus t, or we can just call that t plus 5. So t plus 5 all squared. And then we have here minus 4 multiplied by a, which is 1, multiplied by c, which is 4t plus 8 is equal to 0. Okay, and now all we have to do is solve for t. So square the first term, that is t squared, square the last term, that is positive 25, and then we'll say first term times second term, that's 5t, multiplied by 2, which is positive 10t. And negative 4 times 1 is negative 4. So we're just saying negative 4 multiplied by these two terms in the bracket. So negative 4 times 4t is negative 16t. Negative 4 times 8 is negative 32. So it's equal to 0 and solve for t. So t squared, 10t minus 16t is negative 6t. 25 minus 32 is negative 7 is equal to 0. And now we can factorize this. So equate to 0. T multiplied by t is what gives us t squared. And then factors of 7. 7 is a prime number, so just 7 and 1. But you see that it's negative. So one has to be negative, one has to be positive. Which should be negative so that we can remain with negative 6 in the middle. Make the 7 negative, the bigger factor. So negative 7 plus 1 is equal to negative 6. Therefore, t is finally equal to 7, or t is equal to negative 1. And these are values of t for which h will be a tangent to the graph of f. Okay, so we can see how that will work out. When t equals positive 7, this is where we have h of x being equal to x plus 7, okay, the higher one. And then when it is equal to negative 1, that's where h of x is equal to x minus 1, okay, the lower one. So there we go. Okay, that makes perfect sense. That's where the y-intercept is 7. That's where the y-intercept is negative 1. And that is it for question 6.3. And that is it for question 6. Question 7.1 says, given f of x is equal to 3 over x, we need to determine f prime of x from first principles. Okay, so to find f prime of x, remember that the equation looks like this. Okay, it's to find the gradient of this function. So we clearly still have to find the f of x plus h since we have f of x. Okay, but we'll just find it while substituting. So this is equal to the limit as h approaches 0. And so f of x plus h, to find this, wherever we see x, we just replace it with x plus h. So this now becomes 3 over, we have x, so that's x plus h, minus f of x, which is 3 over x. And all of this is divided by h. Okay, so we have a fraction in the numerator that we have to simplify. Do you see that in this fraction, the denominator here is x plus h, and here the denominator is x. So we're going to have to make the denominators the same so that we can actually subtract them, because in order to add or subtract fractions, your denominators need to be the same. Okay, so they need to be equivalent fractions. So the limit as h approaches 0, we're going to make the denominators the same, and we can do this by finding the LCD, or the lowest common denominator. And really all we're doing is we're trying to make the denominators the same. So we look at this denominator and say, how can we make them exactly the same? Well, you can do that on this side by multiplying this denominator by x and multiplying this denominator by x plus h. Okay, but remember what you do on the bottom, you must do on the top. So we're also going to multiply this numerator by x and this numerator by x plus h. And so that's why our common denominator is x times x plus h. And then our numerator is simply going to be 3x because they multiply. And on top here, we'll have minus 3 multiplied by x plus h. When using the LCD method, it's just a simplified version of this, okay? Because with the LCD method, you just think about what the LCD is going to be and then look at each fraction and ask yourself, what did you multiply to that denominator so that you can get that denominator to look like this? In this case, we multiplied this denominator by x, therefore we must multiply the numerator by x as well, and vice versa. And this also applies to the second fraction. Okay, so this is what we have, and we can just go ahead and simplify. But remember that we're still dividing by h. So here's how I'm going to do this. Because this is now a fraction, I'll just say we're dividing by h. And we can also rewrite h as a fraction by rewriting it as h over 1. So now this is equal to, we have the limit as h approaches 0, and now this is 3x, and this distributes in minus 3x and minus 3h all over. Now with this, I'm going to keep this as it is because I can already see we have an h here, which we can take out as a common factor. And here we have an h, but we're dividing by h. So when we use tip and times, this is going to become multiplied by 1 over h. And you see now we're going to have an h in the denominator that is going to cancel with that numerator of h. So always think ahead of time when working with these problems. So now we have here x times x plus h is equal to, and this is the limit as h approaches 0. And so the 3x and 3x cancel. So now we have negative 3h, and that h is going to cancel with this denominator. Now you see everything that is here, right? It's just negative 3h left. It multiplies with this numerator of 1. And then the denominator multiplies with this denominator of h. So we have hx, we can call it hx, multiplied by x plus h. And now our numerator of h and our denominator of h cancel. And f prime of x currently is the limit as h approaches 0. And all we're left with is negative 3 over x multiplied by x plus h. And now it's safe to substitute 0 in place of h because it will not cause our expression to become undefined. Okay, so this is equal to, so we'll just say f prime of x, and let's get substituting at this point. So negative 3 over x multiplied by x plus, and now this is 0. Okay, and finally, f prime of x is equal to negative 3 over, we know that that just gives us x because it's plus 0. X times x is x squared. And that is our answer. And moving on to the next question. Question 7.2 says 7.2.1, we have to derive the following expression. So how do we derive this function? Well, there's a lot of things that is wrong with it right now. First, we can see that we still have surds, okay? The surds include x. So they need to be written like the way this one is written, okay? So to the power of a rational exponent. And so we're going to do that there. But we also have these two values subtracting, and they're over something in the denominator, which is also a surd. Okay, so we need to fix that. So what we can do is just first of all break them open by rewriting them under a separate denominator, okay, under this denominator each. So we're going to say that this is, we're not deriving yet, so we'll continue writing dx, and we have, and let's just rewrite this as x raised to the power of, so a rational exponent. You're going to say the inside exponent over the outside exponent. And so that is 2 over 3. And then that goes over on its own. So I'm separating those, okay, to let them have that denominator each. So that is going to be x to the power of. And the exponent here is an invisible 1 on the x. And then this is a square root. So this is a 2. So it's inside exponent over outside exponent, meaning 1 over 2. And then this is minus x raised to the power of negative 3 over 2 over x raised to the power of 1 over 2 as well, because it also gets that denominator. Okay, so you know that the way we were able to add them together is because they had the same denominator, and that's why we're able to separate it like that. Okay, if you have 2 plus 5 over 3, you can rewrite this as 2 over 3 plus 5 over 3. Okay, that would just be to expand it. And then let's go ahead and simplify so we can still derive. So these have the same base and they're dividing. So it means that the exponents are going to subtract. So this is x raised to the power of 2 over 3 minus 1 over 2. What is 2 over 3 minus 1 over 2? Well, the denominators are 3 and 2. You can just use a calculator, but we can just multiply here by 2 in the numerator and denominator. And so that's 4 over 6. And then here by 3, so that's 3 over 6. And so 4 minus 3 is 1. So we have 1 over 6 there. So this will become 1 over 6. And then we have minus, and then same thing here. Your exponents are going to subtract because we are dividing by values with the same base. So x raised to the power of negative 3 over 2 minus 1 over 2. So that's going to be negative 4 over 2. But negative 4 divided by 2 is negative 2. Okay, and now we are ready to derive. So we can say is equal to, and we'll use the rules of differentiation. So it's the coefficient multiplied by the exponent, which is 1 over 6. And then we have x raised to the power of exponent minus 1. We can rewrite this one as 6 over 6. 1 minus 6 is negative 5. So this is negative 5 over 6. That's what we get there. And then coefficient times exponent, that's a negative 1 we have there, invisible 1, multiplied by negative 2, and that's positive 2. And we have x raised to the power of exponent minus 1. Negative 2 minus 1 is negative 3. And there we go. This is our expression derived using the rules of differentiation. Moving on to the next question. Question 7.2.2 says we need to determine dy over dx if we have this equation. Okay, so let's go ahead and first make y the subject. Okay, so let's rewrite our equation. We have xy minus y equals x squared minus 1. And we can just take out a common factor of y here first. So y comes out, and we're left with in the first term x, and in the second term, it's just negative y. So it is negative 1. You can always say this term, okay, negative y divided by that common factor. Okay, so this is what we have, and we have x squared minus 1. And then to get y on its own so we can determine dy over dx, we're going to divide both hand sides of this equation by x minus 1. Okay, so we have y equals x squared minus 1 over x minus 1. Now, do you see that in the numerator and denominator, okay, we're going to have common factors because this can be factorized using difference of two squares. So y equals, and we're going to open up two brackets. So this is going to be x minus 1 times x plus 1 all over x minus 1. And so these two would cancel, they simplify, and so therefore y is equal to x plus 1. And now to differentiate this, okay, in respect to x, we're going to say, okay, to find dy over dx, now we're ready to derive. So we'll say dy over dx is finally equal to, and using the rules of differentiation, coefficient times exponent, so that's 1 times 1, which stays 1. And so we have x raised to the power of that exponent of 1 minus 1 gives you 0. And anything to the power of 0 is equal to 1. And you know that if you derive a constant, it gives you 0, okay? Because a constant is really just like a line. Y is equal to 1. This is a horizontal line, and the gradient of a horizontal line is equal to 0, and that's why it becomes 0. Okay, so dy over dx is equal to 1, and that is our answer. Moving on to the next question. Question 7.3 says the gradient of the tangent to the function represented by f of x is equal to ax cubed plus bx squared. So we have a cubic function. At the point 1 and 5 is 12. And 7.3.1 says we need to show that a is equal to 2 and b is equal to 3. Okay, so let's visualize this. We have a cubic function, and just because they said a is equal to 2, we'll just go ahead and show them that this is the cubic function where a is greater than 0, okay, the coefficient of x cubed. And this cubic function has a tangent running to it. Okay, so we have a tangent to this cubic function, and they tell us where this tangent, okay, intersects this graph. So this tangent is at 1 and 5. And this tangent has a gradient of 12. Okay, the gradient of the tangent to the function represented by this at this point has a gradient of 12. And how do we find a and b? So we have two variables missing, but they only gave us this information, this point, and telling us that the gradient is 12. Well, this point has now become powerful because we now know the gradient at that point. And so we can use this information twice. And this is how we can use it. And the reason I'm emphasizing that we can use it twice is because we're looking for two variables. In order to find two variables, you need two pieces of information that can help you form two equations, really. Okay, and this is how we're going to form these equations, despite two things being missing. So this is our function, and we can use this point first as a point having a gradient. Okay, and this is how we're going to do that. Because we know that the gradient at this point is 12, let's find the gradient of this function. So to find the gradient of this function, we derive it. And so this is f prime of x is equal to coefficient times exponent. So that gives us 3ax, exponent minus 1 is 2. Same thing over here. Coefficient times exponent is positive 2bx, exponent minus 1 is 1, and we don't have to rewrite that. So this is the general gradient of this function at any point. But they specifically told us the gradient of this function at the point where x is equal to 1. That gradient is 12. So here's what we're going to do. We'll say that we'll find f prime of 1, and we know what that gradient is. So long we're just substituting that x value of 1. We're saying the gradient of this function at the point where x is equal to 1 is, and we're just rewriting and substituting. And this is all squared plus 2b times 1. And the gradient of this function, okay, where x is equal to 1 is specifically equal to 12. So we'll say 12 is equal to, and we have 1 squared, which is 1 times 3. So this stays 3a, and then that stays 2b. Okay, great. We have our first equation. So we have used this information once. And now the second way we can use this piece of information that they've given us is like this. We've used this point as a point which we know the gradient of, and now we're going to use it as an actual point. So we'll use it as an x and a y value. So on this function, there lies a point 1 and 5. So in place of x and y, we'll substitute 1 and 5. So this is going to be in place of y, f of x, we say 5 equals a times, and in place of x, we say 1 all cubed plus b times 1 all squared. And we just simplify this. So 5 equals, and we have 1 cubed, which is 1. So it's just a plus b. Okay. Now you can see that with this equation, it's easier to make something the subject. So we can do that. Now, at this point, you can decide how you want to solve for this simultaneous equation, because that's what it is. It's a simultaneous equation. Okay. So I'm just going to solve for this by making something the subject here. Okay. So I'll go ahead and make a the subject. So leave a on this side, and we're going to transpose b. So this is 5 minus b. And now I'll go ahead and call this my equation 1, and this one my equation 2. So we're going to substitute equation 1 into equation 2 so that we can solve for b first. So this is now 12 is equal to, and wherever you see a in equation 2, you substitute 5 minus b. So 12 is equal to 3, and then there's a. So that's 5 minus b plus 2b. Okay, and let's simplify further. So 12 is equal to, and we'll distribute. This is 15, and then minus 3b plus 2b, and these would add. So 2b minus 3b is negative b. So this is negative b, but you could just transpose this from the right to the left-hand side. So it becomes positive b is equal to, we still have the 15 on the right-hand side, and we can take this 12 over, so it becomes negative. And so 15 minus 12, we know that that is equal to 3. So therefore, b equals 3. And we've solved for b. Okay, just like they said it would be. Now to find a, you can just take this and substitute it into the equation that had a as a subject, which is equation 1. So a is equal to 5 minus b, but we know that b is 3. So therefore, a is equal to 2. And there we go. We've solved for a and b. Moving on to the next question. Question 7.3.2 says, calculate the coordinates of the points on the curve where the tangent to the curve is parallel to the x-axis. Yeah, okay, so this is one of those long journey to a simple answer. The whole thing about this, right, is just in the wording of how they phrased it. So let's just think about what they're referring to. So they want us to calculate the coordinates, okay, of the points on the curve where the tangent to the curve is parallel to the x-axis. So on this curve, where do we have the tangents being parallel to the x-axis? We know the x-axis looks like this. So where can you ever have tangents parallel to this x-axis? Well, think about that. If it's parallel to the x-axis, we can even just like carry this line parallel to the x-axis and move it all through. You see, it can never be a tangent anywhere here. You can see how it just cuts through here and cuts through there, okay? But the only way it can be a tangent to this curve is right there at the turning point. So at that turning point, it can also be a tangent to this curve, okay, at this turning point. So it's a tangent at this point over here. So this is a fancy way of them asking you to find the turning points of this function. So let's go ahead and find them. So this is f of x is equal to, and let's just rewrite our expression knowing a and b. So this is now 2x cubed and positive 3x squared. And let's find the turning points. How do we find the turning points of a cubic function? We have to remember that really in any curve, we have to keep in mind that at the turning point, this is where a tangent to this curve, or the gradient really, at this point is equal to 0. So it means that the tangent to this curve's gradient is equal to 0 at this point. Okay, so, and it's also equal to 0 there. So we'll find the gradient of this function. So f prime of x equals, and that's going to be 6x squared plus 6x. And when we find the general gradient, we're going to find out where exactly is that gradient equal to 0. So we're making that equal to 0. So 6x squared plus 6x. Let's go ahead and solve for x to find out where this happens. So you can see that we have 6x in common. So we can just take 6x out as a common factor and we're left with x. And in the second term, you'll just be left with, so 6x divided by 6x is positive 1. Okay, and I'll just put the 0 on the right-hand side. So something multiplied by another thing gives you 0. It's either the first factor is equal to 0 or the second is equal to 0. Therefore, x is either equal to 0 or x is equal to negative 1. So these are the x values of those turning points. The x values where we have the gradient of the tangent being equal to 0. But they want the coordinates, the full coordinates. So let's go ahead and find them. So we're going to have to take the original function and we'll take those x values and we need to find their y values. Now with the 0, that one is quite simple. You see that if you substitute 0 here, it's also going to give you 0. Okay, so in this case, this is an x and a y intercept at the origin. So we know that f of 0 equals 0. Okay, and then if we substitute that negative 1 in, we're going to get 2 times negative 1 cubed plus 3 times negative 1 squared. And we know that if you square a negative value, it becomes positive. So that's just going to stay 3. But this one is going to stay negative because it's cubed. So 2 times negative 1 is negative 2. And so 3 minus 2 is 1. Okay, so those points are 0 and 0. And the second point is negative 1 and 1. Okay, and that is our answer. And that is it for question 7. Question 8, 8.1 says, the following information is given relating to a cubic graph f. And they're giving us a whole lot of information. So let's see. They say that f of 0 is equal to 0. So this just means that on the graph of f, we have a point with an x value of 0 and a y value of 0. Okay, so that is a x and y intercept at the origin. And then f of 3 is equal to 0. Okay, a way you can do this is to just draw a small sketch of the graph just so that you can follow what is going on. It will probably help you with the final question that they want you to tell them. Okay, they want you to explain the meaning of this. So we have a point first at the origin. the x value is 0 and the y value is 0. So 0 and 0 is a point that we have. And then they tell us we also have another point, f of 3 and 0. So the x value is 3, the y value is 0. So this is 0, and then we have 3 and 0. Okay, just moving it more to the side. So now we have 3 and 0. And then they say f prime of 3 is equal to 0. So at this x-intercept, we have a turning point because f prime means the gradient, and they said of 3. So the gradient of this function where x is equal to 3 is equal to 0. We know that the gradient will only be equal to 0 on this cubic graph where we have a turning point, because that's the point where the graph is standing still. It's no longer increasing or decreasing. Okay, that's a stationary point that we have. Okay, so we know we have a turning point over here. And then, so it could look like this, or it could look like this. We'll see, okay, whether it does this like that, or, does that. Okay, so from here, that's what I'm getting from that. And then they say f prime of 1 is equal to 0. So we have another turning point at 1. Still doesn't really change that. It still could be either of these so long. Okay, because f prime of 1, meaning you could have another turning point there that is a local maximum, or another turning point that is a local minimum. And reading forward, now they tell us that the second derivative, okay, where x is equal to 2 is equal to 0. You see, where the second derivative is equal to 0, this is where you're going to find your point of inflection. And that is that point where the graph changes concavity, meaning it changes from concave down, for example, to concave up, or it could be changing from concave up to concave down. So that point would be somewhere here. Okay, so in between these two. So at 2, there's a point of inflection. It could be here, could be here. We're still looking at the shape of the graph. So long with all of this, this is what we have, including this. And then they say that the second derivative of this function is less than 0, meaning it's concave down for values that are greater than 2. And this is going to help us to pinpoint what exactly this graph looks like. So the second derivative where x is greater than 2, so over here, from here onwards, where x is greater than 2, that is less than 0, meaning it is concave down. Okay, so if it is concave down here, then we know that this is what the graph looks like. It's not this one. Okay, so the question is really just explain this. And from the beginning, I already said, it just means that the graph is concave down. Or it could also be, so I'm just going to say here, we can say this means that the graph is concave down. So we can say f is concave down where x is greater than 2. Okay, so where x is greater than 2. Another thing they could be pointing at, okay, because when they tell you about that point of inflection, but they also told you those turning points, it could also be telling you what type of turning point you have, whether it's a local maximum or local minimum. The two turning points we had was the one at 1 and the one at 3. Okay, so f prime of 1 and f prime of 3. So because we're looking at the values where x is greater than 2, that could be pinpointing that this turning point is actually a local maximum. This is a local minimum because it's below, and this one is above it. Okay, so yeah, that could be it. We could also say that f has a local maximum at f of 3 equals 0. Okay, so these are two possibilities that they could have been referring to. I'd actually more go with this one just because, they were specifically showing us that that graph is concave down. Okay, so that is it for that question. Moving on to the next question. And then 8.1.2 says draw a neat sketch of f showing all relevant points. So see, we didn't really need this, but this was just for explanation. Okay, so we can already see what that looks like. Let's just draw that down neatly. Okay, so this is what our graph just looks like the previous question. Okay, and showing all relevant points. So we can see that that's an x-intercept, that's another x-intercept. This is a turning point, so you can just show that, yeah, we have a turning point, okay? And this is another turning point, but it's also at the x-axis, okay? So we have 2 there. This is a point of inflection, Okay, and that is our answer. Moving on to the next question. Question 8.1.3 says, determine the values of x for which f prime of x multiplied by f of x will be less than 0. So the graph we have currently, and I should have actually named this f, okay? The graph we have is f, and how will f prime of x look if this is f? So you see here, you really have to study your cubic function and its relationship between its derivative and its second derivative, okay? And all of that information. So with f of x, this is f of x, and with f prime of x, if the graph looks like this, okay, then it's like a backwards n, meaning that the value of a, the coefficient of x cubed, is negative. If you derive this function, it's going to give you a parabola, but because a was negative, it's going to give you a concave down parabola. So now we just need to think about how that parabola is going to look here. It's a parabola, it's concave down, but there's specific special points we need to note. That parabola, it's going to have two x-intercepts, and those x-intercepts are going to be at the same x values as your turning points of the original function of f. So it's going to have an x-intercept over there at 1 and at 3, since those are the x values of the stationary points of the cubic function. And then another important point, you see this point of inflection at 2. That is where our parabola's turning point is going to be as well. We will find it at x equals 2. So let's just say it looked like that, right? And so we're going to have this graph like this, intersecting at 1 and intersecting at 3. Let me just try to draw it nicely. Okay, so this is f prime that we have. And now we need to show them where f prime multiplied by f of x is less than 0. So these refer to the y values of these graphs. So where will the y values of f prime, if we multiply them to the y values of f, where will they be less than 0? Okay, so now we're just looking at numbers. Where we can get values less than 0 when multiplying is if this f prime of x, okay, if those y values are positive and we multiply them by these y values which happen to be negative, then they will give us a value that is negative. That is a value less than 0. And then another way that this could happen is if the y values of f prime were negative and then they multiplied by the y values of f and they were positive, then they would also give us a negative, a value less than 0. Okay, so we're just looking for these. So where does these graphs meet this criteria? So when you're looking at whether they are positive or negative, this refers to the y values. So here you have positive y values, here you have negative y values. So we're just going to look for where the graph of f prime is positive, and for the same x values, the graph of f is negative. Okay, so I'm going to use this vertical line so that we can just watch and monitor this. Now, I noticed that when we are on this side, okay, the graph of f, okay, that black graph over there, it has negative y values, okay, starting from that point at 0, when it goes beyond that, below that, okay, the x-axis, then it has negative y values. Now, if we're going to compare it with the graph of f prime, so I'm just going to go ahead and start with this one instead of this case, because I can see that f prime of x has negative y values here. And so for the same x values, the graph of f must have positive y values. But you see what's going on here? This has negative y values. Great. This also has negative y values, so we can't take that. So we'll keep moving and just keep checking where we can see them. Here they both have negative y values because they intersect at this point. Keep going. And here the graph of, and this is actually a very important point. Now do you see that at this point, the graph of f prime hits the x-axis. At that point, its y value is equal to 0, right? While this graph of f, its y value is negative. When we go beyond this, more to the right, you can see now that the graph of f prime has positive y values, while the graph of f of x has negative y values. So this is actually, we can actually start with this. This is meeting this criteria where we have positive y values for f prime and negative y values for f. Okay, so that is valid all through here. So here it has positive y values, and here it has negative y values. And this one keeps having negative y values until that point at x equals 3. So we can see that it works all through here for these two graphs. Okay, f prime is positive while f is negative below the x-axis. So we can tell them this happens first where x is. So say x is greater than, okay, so starts at 1 and then all the way to 3. So greater than 1 but less than 3. Okay, so that's the first one we have. And then do we have this criteria being met again? Well, definitely not anywhere here, because then after this, do you see that after 3, both graphs are just negative? See, they're both below the x-axis. So we can't even take that. Now, there's something we're missing if we just ignore this part over here. Yes, here they're both negative. Okay, that has negative y values. It's below the x-axis. This also is below the x-axis, negative y values. But if we decided to go here, okay, do you see that here, this is where the graph of f starts having positive y values. It's above the x-axis. And this graph, it's a parabola. It's going to shoot down like that. So it's going to have negative y values, meaning it's also going to work all through there as well. So we're going to have to include that and say it also works here because this graph is also going to shoot down. Just the way I drew it, it's supposed to kind of do that. It's like down, okay? So it will also match there as well. Okay, so we can see that also happens for values that are less than 0. Okay, so it's this, or we can say x is also less than 0. Okay, so to write it in order, I'm just going to put where x is less than 0 first, because we're writing it from left to right, or where x is greater than 1 but less than 3, and that is our answer. Moving on to the next question. Okay, question 8 says, if it is further given that the graph of f passes through point W, which is 5 and negative 40, determine the equation of graph f and leave your answer in the form of, so f of x equals px cubed plus qx squared plus rx, where p, q, and r are constant values. Okay, so they just want us to find the equation of f with all the information they've given us and this new point W, which lies on the graph of f. Okay, let's see how we can do that. Let's just see what this graph looks like. Okay, we are at an advantage here. Why? Because this is that special type of cubic function that has a common x-intercept and a turning point. And here's the thing about that graph. We can actually write its equation like this. So we'll say f of x is equal to, because they said px cubed, that's a coefficient of x cubed, I'm going to call that p. So we can rewrite it in the x-intercept format. So we'll say x minus x1. Now this x1, the one that gets squared, right? That is the one that is sharing a turning point and an x-intercept, where you have a turning point and an x-intercept at the same time. And we can see there that x1 that we're referring to is 3. The other x-intercept we have is at 0. Okay, so I'm just going to say x minus x1 squared times x minus x2. So whichever is squared, that is the one that takes that common turning point and x-intercept. So I know that x1 is 3 and x2 is 0. Those are the x-intercepts. And that one is also a turning point. So I'm going to rewrite this as f of x is equal to, and we have p multiplied by x minus 3 all squared times x minus 0. Okay. And now do you see that we're almost done? Okay. X is empty as usual. Y is also empty, but it's just p that is missing. So all we have to do is substitute one point on this graph that will help us to find p. And they gave us a point, W. So we'll say W is 5 and negative 40. Okay, so we're going to say negative 40 in place of y is equal to p multiplied by, and then in place of x, we're substituting 5. So that's 5 minus 3 squared, and then 5 minus 0. Okay, let's simplify and solve for p. 5 minus 3 is 2. 2 squared is 4. And then 5 minus 0 is 5. So times 5. That gives us 20. So this is 20p is equal to negative 40. And then divide both hand sides by 20. Therefore, p is equal to negative 2. Okay, now all we have to do is substitute this into the equation that was almost complete. It was just missing a p. Okay, so now this is f of x is equal to, and we'll say this is negative 2 times x minus 3 all squared times x, because that's just x minus 0. Now, you can actually rewrite this x in front of the 2 since it's just multiplied by everything here. Okay, and this is still protected in brackets. So this is negative 2x. And now we can just simplify it so that it's in this format, and then we can easily see the value of q and r. We already found p. So this is f of x is equal to, and we have negative 2x multiplied by, and distribute. We square the first term, which is x squared, square the last term, positive 9. First times second is negative 3x, then times 2 is negative 6x. And now we can just distribute there. So finally, f of x is equal to negative 2x cubed plus 12x squared and minus 18x. So remember, this is p, q, and r. So we can clearly see now, therefore, p is negative 2, q is 12, and r is negative 18. And that is our answer. And that is it for question 8. Question 9 says, an industrial chemical is stored in rectangular containers with a square base. Okay, so this is one model of the container. Okay, and the square base has x centimeters. So x as the side and the other side of the base. The height of each container is h centimeters as shown on the figure below. The volume of each container is 2,160,000 centimeters cubed. And 9.1 says, determine the height of the containers in terms of x. Okay, so they've given us the volume. And to determine the height, we can think about how volume is calculated because it will include the height. So volume is equal to the area of the base, and the base is a square, so that's going to be side times side, so x times x, which is x squared, multiplied by the height. Okay, it's always area of the base. You can find the area of the base, and then you multiply it by the height, you will get the entire volume of the shape. Now we already have the volume. It's 2,160,000. So 2,160,000 is equal to, we don't have this, we're just trying to find h. Okay, multiply by h. And so to get h on its own, so it can be in terms of x, we can divide both hand sides of this equation by x squared. Okay, and that will get h on its own. So therefore, the height is equal to 2,160,000 divided by x squared. And that is our answer for the first question. Moving on to the next question. Question 9.2 says, for safety reasons, during the transportation of the containers, a triple layer of material is needed at the base of the container. Okay, so we just need to see what this will look like. They say ignore the thickness of the material, gladly, because that would complicate things. And they want us to show that the total surface area of the material used for the container is given by this. Okay, so let's just take this image quick and then see what this will look like. Okay, so this is our container, and all they're saying is they're going to add a triple layer of material, okay, at the base. So this is what the base would have looked like. Normally, we would just need a layer, okay, of material because they're going to cover it with something. Clearly, that's what they're saying. And if we're going to put a triple layer at the base, it just means this base should have 3 of whatever it used to have. So it used to just be x by x, and now it's going to have another layer and then another layer as well. So we're now going to also have to account for the material that will be used for those 2 added layers. So including this one, it's now 3 layers at the base. Now, I don't really know what material they're using. Maybe they're painting it, okay? But if we're adding some sort of material, okay, around this object, around this, and they're telling us show that the surface area is this, we're just trying to find the surface area of this entire shape. So let's look at the areas that will be covered. We're going to cover the top, which looks exactly like the bottom. It's also just x by x. We're going to cover the bottom, so it's that first base, and then the two other bases as well. So we have a total of how many of these squares, these x by x squares. We have this one on top, 1. We have the first base on the bottom that we already had, that was 2. So this one is 2. Then we have these two added ones, since we must have a triple layer, okay, base. So that is 3 and 4. So we just know we have 4 of these shapes that we need to consider. And then with these shapes that we have here, these rectangles. Okay, so we have that first rectangle, and it's an x by h rectangle. So that's 1. And then we have the one on the side, 2, the one at the back, 3, and the one on this side, 4. So that's what we're just putting together. So we're finding the areas of each of this and accounting for how many of those shapes that we have. Okay, so the total surface area would be equal to, we will say, let's start with those bases. We have 4 of them. So it's 4 multiplied by x times x, which we know will be x squared. So that's all those bases that we have, and the top, of course. And then plus, and then these blue ones, these rectangles, we have 4 of those as well. So that's going to be 4, and the area of each of it, its length is h and the width is x. So that is h multiplied by x. So let's just substitute, because we already have a value for h. This is in terms of x. So that's all we have to do. So we can finally call this a of x is equal to, and this will be 4x squared. And then, well, you see, that's not 2 terms. It's 1 term. It's going to be xh. So let's just rewrite this as, because we know we're substituting in place of h, we can just call this 4x multiplied by, and then the h is this number, okay, 2 million, and then that, and we just have to simplify this. So therefore, a of x is equal to 4x squared, and when multiplying, you see, we're adding to this. So this is a term on its own. And so we're multiplying these two values together, meaning diagonally, do you see that we have a common factor of x? So that will cancel, x cancels here, and one of the x's cancel here. So 4 multiplied by that number, let's just get that. 4 times 2,160,000, and that is 8 million. Okay, so we're going to say that this is added by 8,640,000 over x. Okay, and then just see, is that what they have as well? Yes. Okay, that is our area. And moving on to the next question. Question 9.3 says, we have to determine the dimensions of the container that will ensure that the minimum amount of material is used when making the container. So what we are seeing as the material is the total surface area, because that's what goes around this material. Okay, and we just found that the total surface area is this. Now we need to find the dimensions. If they're saying dimensions, they don't just want the values of x, okay, because the x was those dimensions for the base and of course the top part of the shape. But this will also include the height. So the dimensions just means you need to find x and h as well. Okay, so find the values of x and h that will ensure that the minimum amount of material, we already know that the material is now referring to the surface area. So find the values of x and h for which the area, this will be a minimum. We can see now this is a maximum and minimum problem. So we're going to take the area that we have and we're going to find the x value at which this is going to be a minimum. You're trying to find a minimum or maximum value. Okay, works like with a turning point. When you're trying to find the minimum or the x value at least at which this is a minimum, Remember that at this point, this is where the gradient is equal to 0. Okay, it's no longer decreasing or increasing. So that's what we're going to do here. Let's find the gradient of this function. Now, do you see that to find the gradient or to derive this function, we have to move this x up to the numerator because we can't derive like this. So we'll rewrite our function. This is equal to 4x squared, and we're going to say plus 8,640,000, and now it's x raised to the power of, its exponent was 1, so it becomes -1. And now we're ready to derive. So this is a prime of x is equal to 4 times 2 is 8, so x raised to the power of 2 minus 1 is 1, and you don't have to rewrite that. Coefficient times exponent, that is -8,640,000, and then x raised to the power of exponent minus 1 is -2. Great. And now we can make the gradient equal to 0, the derivative equal to 0, so we can find that minimum value. So this is 8x, and then we have -8,640,000. And I'm just going to go ahead and rewrite this so that its exponent is positive. So it's currently in the numerator. We move it to the denominator. And so it's x squared. Okay, this is negative. We can just transpose it to make it positive. So it's now positive 8,640,000 all over x squared is equal to 8x. And now just cross multiply. X squared multiplied by 8x is 8x cubed is equal to 8 million. So this has a denominator of 1, so they multiply. 8,640,000, and now we can solve. So just get rid of the 8 by dividing both hand sides of this equation by 8. Let's see what that gives us. We already had this number, so divided by 8, okay, and so x cubed is equal to 1,080,000. And then we can cube root both hand sides of this equation. So cube root, this doesn't work like square root. You don't have to consider the positive or negative solution. So x is simply equal to, we'll take this, and we're going to cube root that answer that we got. You just make it simpler. Okay, now just to ensure that this is correct, I'm just going to find the cube root like this. So the cube root of 1,080,000. Okay, and you can see what it gives us. It gives us 60, the cube root of 5, okay? And in decimal form, well, you can't leave it like this because you have to round out to 2 decimal places either ways. So that is 102 point, and that is going to round up, making that a 6. So 0.60. And then with this, we can find h. So you need to find the dimensions, so x and h. So how do we find h? You can just use the equation for h. So take this and substitute in place of x, and we'll find this. At this point, you can decide to either use this rounded off answer, or you could use that. I would actually just use the more accurate one and then just round both answers off to 2 decimal places. Okay, so that goes all over 60 cube root 5 all squared, and let's see what we get. Okay, so the answer of h there is 205 point, and that 7 is going to round that up, and then it goes to that one, which becomes a 2, so 0.20. And they're both in, what were these in centimeters, because this volume was in centimeters cubed, okay, as we saw in the first question. So we can finally say that is centimeters, and that is centimeters, and that is our answer. Okay, so those would be the dimensions if a minimum area, okay, were to be used. Okay, so those are our answers for question 9, and that is it for question 9. Okay, so that is the last question, and that is it for this paper. I hope you guys enjoyed it, and I will see you guys in the future videos.